I'm not 100% sure, but I know like um, Korea is really putting a lot of effort into doing robotics and AI. China is also um, see, the thing is, I'm an educator, and then I see the countries that invest a lot of effort and money into educating students to be able to do robotics and AI. And then I'll say Korea and China are the leading countries at this point. But I'm not 100% sure because I don't know all the countries in the world. I might be biased because I'm Asian, but I'm sure that India is gearing up as well. I think that education is really a key for the future um, success. And then I'm really excited to be actually invited to talk. Um, Thank you so much.
Thank you so much,
Thank
Professor.
you
I
so
mean,
much.
thank you for your nice talk, and it was like brief and crisp, and it shows us like what is the effort for robotics to be children in developing countries, and the effort which are laid uh, regarding this. And I can see that the time at your end is 1 a.m. Approximately 1 a.m. Right? Thank you for your
No,
nice
it's
talk.
actually 10:30, so not.
10:30. Okay.
Yeah, okay.
Okay. Okay. So thank you so much for giving your valuable time, and
Thank you. Thank you
we
for
look forward.
inviting.
Thank you. Thank you so
Yeah.
much. So
And then I put my email address, so there's any questions, please feel free to email me.
in the brochure we have the email address.
Okay, great. All
Okay.
right.
It's
Thank
good that
you.
you provided to everyone. Yeah. Thank you so much.
Thank you.
So I would like to invite the next speaker, who is myself. So thank you so much. My presently I am a research fellow with Prof. Mohan in SUTD, and I'll be presenting on the topic of taxonomy of self-reconfigurable robots. So hope my screen is visible to all, and yeah. My presently I am a research fellow with Prof. Mohan in SUTD, and I'll be presenting on the topic of taxonomy of self-reconfigurable robots. So hope my screen is visible. So as our lab have the design philosophy of self-reconfigurable robots, so let me just give a brief overview what self-reconfigurable robot means. That they are autonomous kinematic machines with variable morphology. By variable morphology, it means it can change its shape as per the environmental needs. These are some of the earlier development from uh, in the form of CE-bot, Polybot, MTran. So these can the multiple modules can assemble together and disassemble together to perform a particular to take a particular shape. And these are some more development at e-tron, Superbot, Roombot. So the advantage of these self-reconfigurable robots is that they can evolve over time. It has a multi-functionality and it can survive. So with these robots, most of the lab works in the area of development of mechanism, control, and artificial intelligence. But very few are exploring the application aspect of the self-reconfigurable robots. So in our lab, our focus is to develop these self-reconfigurable robots from scratch and also implement it for some use cases. So one of our development is in the form of tiling robots, which is the application aspect of the self-reconfigurable robots, designed to change its shape. As you can see, it can take different reconfigurations. And the advantage with this in its application is like it has a larger coverage area. In the left, you can see the Roomba robot, which cannot access the spaces, but these self-reconfigurable robot can change its shape and can access those narrow passages. And in this, we are comparing the area coverage between fixed form robot and flexible morphology robot that can change its shape. So this work was presented by one of our team member in ICRA 2017, and so we have, after this we have lots of versions which at present we are also including the floor cleaning modules in it, so that mopping and vacuum cleaning is now integrated in these modules. We are also having a different shapes as well, which, like you can see over here, this is a triangle shape, hexagon shape. So overall, the whole team is working on different aspects of these styling robots. At present, we are also including the floor cleaning. Then one of the development from our lab is now integrated through the reconfiguration. We are trying to cover the glass facade for glass facade cleaning. So this robot has capability to transfer from one glass panel to another by lifting one module at a time. So this robot is able to cross over from one glass panel to another, so no human intervention is required to shift from one panel to another. And these are omnidirectional robot. The adhesion principle is based on the suction created by impellers. So this prototype was developed by Dr. Manuel, who is also one of the speakers tomorrow. So, and he was with Road Lab, and this development was under his team. And you can see in the left, there are multiple versions which evolve for a given task. So when we design a robot, it's not like one is fixed. The design evolves over time, and we need some of the method to quantify in which direction it is evolving. So that I will explain that how we can quantify different versions of it. Basically, how we can compare the two versions that we developed in the same lab or compare with different robots. I will just quickly show one more video that we have developed in Road Lab. Is Scorpio, which is a bio-inspired self-reconfigurable robot which can crawl, roll, and climb wall. So this, you can see that the robot is capable of climbing wall by adhering to the surface. The assumption is the surface needs to be flat and clean, and we are using passive adhesion to it. So gecko tapes are used. And over here you can see it can change its shape to revolve robot, which can crawl, roll, and climb wall. So this, you can see that the robot is capable of climbing wall by the transformation can take autonomously, and the assumption is the surface needs to be flat and clean. The different gate pattern, and we are using passive implementation to it. So gecko tapes are used. And over here you can see it can change its shape. This was developed mainly for reconnaissance tasks or surveillance tasks. So this, you can see that in our lab our focus is climbing wall. By have the transformation concept of self-reconfigurable, and the assumption is the surface needs to be flat and clean with that pattern, and we are using passive implementation tasks, gecko tape sections. And when you can see it can change its shape. This was developed mainly for reconnaissance tasks or surveillance tasks. So this, you can see that in our lab, overall observation that we could have made of the previous video is like there are different mechanisms involved for performing the pattern, and we are using different autonomous section. It is and when you operate it, was handling it for the mainly autonomously acting, then we have a different scale of it, like the size. Functionality observation that we have there was a question that how to quantify these mechanisms was there under the taxonomy of but in short, what we how taxonomy differs from classification. So that classification is systematic arrangement of category or particular established size. We have established and classified a how it is like and what it costs based on size, what how taxonomy apart from that, that as well, how it can compare the size. And that's my extending the beneficiary application combination but it depends on the size of the changes how it can come together and perform functions like we can see how it has nested advantages and that's my like extending the beneficiary application combination
that there are areas in which silicon is actually better than nature. So one example is energy. But of course, it's not all bad. There are areas in which silicon is actually better than nature. So one example is
Hello.
Okay, so are you also planning to quantify your results, like how much safe it is? What are the parameters, and how you planning to quantify your safety suggestions, or the framework? Basically, framework. Uh, what I mean, uh, what generally public mean is like it should cover a mathematical basis to quantify. So it should not be only uh, uh, subjective, but it should be objective in terms of
Yeah.
like quantifiable numbers. So,
Yes, Amir.
what are your
Yes,
plans for that?
correct. Yeah, it should be a quantifiable numbers. When I say quantifiable, it comes from the KPI, key performance indicators. So these key performance indicators are numbers. So every sensor, every component of the robot will give a mathematical value, and those mathematical value are captured as part of either key risk indicator, or it could be a critical success factor. So if this is within a threshold limit, so there is a definition of a threshold limit. So every KPI, every attribute would have a threshold limit. And these threshold limits are the numbers which is used to measure. So if you could look at this, there are two different points. One is the heartbeat, which is nothing but the KPI value that comes from the robo. And the another one is the threshold limit. What is the threshold limit within which the robo should be operating? Every component should be operating within that limit. So that is the number. And the breaking point is another number. So any number, any KPI value that goes beyond a breaking point is a problem. It goes into danger zone. Anything that goes beyond the threshold limit, it's another number, that's a comparative number, which will be onto a warning zone.
Okay.
Okay, there is a question which I could see from Mr. Naveen Kumar. It's KPI variation methods to easy learning. Yes, so KPI is a key performance indicator, which will have every component will have a from the robo. We can pick up every component that is required for us to monitor, and every component will have its operating value and its a threshold value. It's a breakdown value and it's a threshold value. So based on that, we can do that, and it is easily learnable. Hope it answers, Naveen Kumar. I got another question from Mr. Sanjay V. Nair. So his question is, what is the significance of deep learning in connection with safety in robotics? Okay, deep learning talks about algorithm or the function which has been the software which is there in the processing unit. So what we are talking about safety, to feed the information into the deep learning, there should be some KPIs. There is a measurement which you need to take, and these are the measurements to keep the robo within the safe zone. And these measurements will be fed into deep learning, and deep learning would help to keep the robo within that safety. So an action that need to be performed post deep learning will be like, whether the robo should be stopped or it should be informed. There should be a message that should be sent to a support unit. So those are all the actions that would be based on the outcome of the deep learning, which has been fed by these KPI values. I have another question from Rizwana Parveen. How the system discuss between the heartbeat signal as in robo. We have multiple variety of sensors. Each sensor has a different signature. Okay, so this is a good question. So as if we have a human has one heartbeat. I mean, we have one heart and we have a beat there. But however, if you look at it, we have different sensors. We have skin. We have different sensors at different parts. So similarly, a robo will have a signature, or rather, a signature need to be built in the robo so that every sensor is going to provide different signature to the processor, and the processor should be able to identify based on the signature what is this sensor, where the signal is coming from, which sensor, and based on that signature, processor will be able to periodically verify, or rather, it's going to continuously monitor the heartbeat, and if the heartbeat of a specific sensor did not come, it can act on it. I have another question from Ketan. Why don't we establish robots here in India, in all hospitals, to take samples during this COVID-19 pandemic? I'm sorry. I mean, I don't know. I don't have an answer for this. Yes, robots can be employed in India. I mean, to my knowledge, I have read an article that there have been many robots that has been deployed in China, where the patients, the COVID patients who have been kept into a separate room, so they have been served with their medicines and their food by robots. But yeah, that can be done in India as well.
Thank you, Naren. Thank you so much. And related to the previous question, it's the responsibility of like all of us, especially the researchers, and so that they can build the robots and then do the deployment. So this is what this webinar is also focused at, to give the exposure that what is going on and what can be implemented. So I hope like Ketan is a researcher, and you can also start contributing towards some solution related to this pandemic to help it out. Uh, so we have our next speaker. So thank you, Naren. Thank you so much for giving us the outline on the safety aspect of the self-reconfigurable robot and linking it to the human system, which is more easy to connect. Like you have sent a heartbeat, so and correlated the sensors in the robot with the human sensing capacity. So when we sense anything out of the way signal, then we react to it, and our brain react to it. So the bio-inspired safety aspect implemented in these self-reconfigurable robots will is a nice idea. So all the best for your future work in this direction. So
Thank you.
thank you.
Thanks so much.
Now,
Thank you.
now we have our next speaker, Mr. Mr. Arnab Sinha. He did his PhD from IIT Kanpur. Thereafter, he had been in a postdoctoral research at University of Rome and at SUTD and NTU for 2.5 years in robotic vision. So his expertise is into robotic vision. And after an almost 2 years stint at Samsung R&D Noida, India, he is currently working as a scientist at a TCS Innovation Lab for almost 3 years. So Tata Consultancy Services has their robotics innovation lab across different parts of India, and one office is in Noida, and in Kolkata, and in Chennai. So he has several reputed journal and peer-reviewed conferences publication. He also submitted 4 patents during his stay at TCS. His objective is to educate young minds for the rising future of robotic world. I would like to share the presentation to Mr. Arnab. screen now. Now you can share your screen, Arnav, Mr. Arnav. Thank you for agreeing on giving a talk. So, Arnav, next to you. Yes.
Hi, good afternoon, everybody. I think there is some noise.
Arnav, can you hear me?
Yeah, I can hear you.
Okay.
I think there is some noise is coming.
No, no, it's okay. Now is okay. I think now you can. Is okay now, right?
Yeah, yeah.
Yeah, perfect, perfect.
The
Okay. So, Dr. Arnav, next to you. You can share your screen for your slide.
yeah, something is not working. Just a minute.
Arnav is okay from your end. Hello, Dr. Arnav. Arnav left. Again, right. So Dr. Arnab is having some technical uh, problem in uploading the slides. So meanwhile, we can have the again reminder as an objective of this webinar is we are thankful to all the speakers who agreed like on continuous back-to-back presentation, and it is like fully lined up on enabling technologies and emerging robotic use cases. And moreover, we have a speaker from around the globe, and they are presenting a different aspects of robotics application in our life. The the thing is, we might not uh, uh, get the whole technical details of each presentation, but it is to get aware what people are working and which area we can more contribute in. So as a participant, our uh, objective is to look at our key area of interest and try to learn as new concepts which are being presented by a distinguished speaker. Meanwhile, Arnab is setting up his available. No. So I would like to ask one of the audience, like so far, what they feel about the presentations made by Dr. Ami Eguchi, our first speaker, then Dr. Garrick from Intel, Dr. Madan, then Naren. Anyone from the participant can comment on or give the how what they like in the presentation so far. So they can open their mic, and then anyone from the priest side as well, or any audience. So Arnab is asking for another 2 minutes. So we can have some comments from our base side. I'm a student of Robotics and Automation Engineering, PGS College of Technology. This program was very useful for me to know all about this. Yes. Any other, even if they can, if they want to speak apart from writing, they can open their mic for a while and then they can speak.
Mr. Amir, I would like to.
Yeah, I am here.
Okay, thank you. Now you are here, so just give me a second.
Hello. Mr. Amir.
Yes, we can listen you. Dr. Arnab is here. He is the next presenter. He has joined the meeting box, so he is now. He will now share his screen. He is the presenter. Thank you, Arnab.
Yeah, hi. Good afternoon, everybody, and thanks for the opportunity to give the lecture. I hope, am I audible to?
Yes, the voice is clear.
Okay,
and you
so
have shared the screen. We can look at your screen as well. Yeah. Yes.
Okay. So yeah. So you can see my screen right now?
Yes, perfect. Robotic vision, past, present, and frontier.
Yeah. So I've been within this robotic vision like for last almost 12 to 13 years. So this is it's very short time to present all these topics inside 30 minutes, but I will try my best. So first there'll be an introduction, what is robotic vision, what I meant by that, and some what has been done, what is currently going on, and what are the research challenges that we are actually looking forward to. So robotic vision. So robotic vision, we all know about computer vision. So I refers only to research works which deal with monocular camera or RGB, like color camera, depth camera, or thermal camera, infrared, such cameras, where you have uh, mostly 30 frames per second, and you wanted to perceive or you wanted to calculate the 3D world, what is there, uh, what objects, what is the 3D world shape.
Uh, Dr. Anam, are you speaking something? Because we cannot hear your voice at present. Hello. Anab, are you there? Hello.
Yo. So other than SLAM algorithms, the robot cannot move. And these SLAM algorithms right now has been solved previously with the help of different kind of sensors with different kind of algorithms. And right now the work is going on in sensor fusion algorithms. So not right now, like last 5 to 10 years is the work is going on. Coordinate frame, and you know that where you are, and the robot has to know this kind of information with respect to its own world coordinate system. So it has to know that. And mathematically speaking, it's like given two sensor data in 2 or 3 sensor data in different times, you need to associate you know with respect to one dataset to another dataset how the robot has moved or not moved. So how much it has moved or where it has moved with respect to one initial frame. And mapping is something like you if you have an exterior sensor like camera, leader, this kind of sensor, not the uh, uh, interoceptive sensors. Like IMU is only measurement. Like if you close your eyes, then IMU is the one that is guiding your movement. And tactile also. Tactile is a touch sensor, so you can touch and move around. Still, you can localize, but it's not very accurate. But mapping is something like you need some representation of the environment around you, or in this case the robot or the sensor, so that it can easily localize itself with respect to this environment, and also it can know that where to move. Like I'm sitting right now in front of my desk. If I need some water, I have to go up and move to other table and pick up the water. So I need to know where I need to move. So that is called a representation of the world, and you also need that for the robot to move around within the environment. So it's just an example with a 2D leader. So leader is a laser data. So you can see in the screen, uh, the blue dots is just some points that has been scanned from the environment. It's a planar leader. So you have 1D leader, which is just on a rotating platform, or there is a rotating mirror in front of the leader, which gives you this point cloud data. And when you move the sensor itself, uh, then this is the sensor. So when you move the sensor itself, you get another data set. Then you kind of know where the data is coming from, so you kind of localize very quickly. And if you know the localized information perfectly, then it's very easy to create the map. You just join these two data points together and you create the map. So it's a chicken egg problem, and people have come up with various algorithms. There are multiple algorithms, and with respect to different sensors, you have different kind of algorithms. Like in case of leader, 2D planar leader, you have scan matching algorithm. You when you move to 3D point leader, you get 3D picture of the scenario, and you move the sensor, and then you see another snapshot, 3D snapshot of that scenario. Then you can use another algorithm like ICP algorithm or other algorithms, which just yeah. Am I audible? Hello.
So you are audible, but it is breaking somewhere.
Okay. Okay, but is it understandable?
Sometimes, only sometimes it breaks.
Okay, 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 okay. So if you cannot follow, just let me know. Okay, thank you. So yeah, so people have developed multiple algorithms with respect to different kind of sensors. Like if you have a monocular camera, then the problem definition and the solution gets totally different with respect to leader, where you have the 3D point cloud data, you don't have the image. And with respect to IMU, like inertial measurement unit, where you have only gyroscope data, you have magnetometer data, you have accelerometer data, you have
Your audio has break. Hello, sir. You are not audible.
use IME, then it is really hard to localize yourself. It drifts very fast, and when you rotate yourself, then the drift is much more. So usually IMU is used for localization with either other sensors like GPS data or something else, just to make it uh, not drifting. So right now, um, I am talking about only the past history of the robotic vision. So with respect to camera, you have pure computer vision. So here you have different camera images at different time taken. Their first is basically known structure from motion algorithms. There is a very huge research going on in this till now because it's never perfect. And with structure of motion, these are the classical algorithms. So you have mainly 4 steps. First step is to identify some critical features, which is usually the corner features, usually. But right now with deep learning, you have a feature set which can be learned also, which you don't have any control of it. It depends upon the optimization problem definition. So classically, you start with the corner features, then there are some other features like off features. Off slam is actually made with disk feature is there, there is shift features, surf features, all these features are there. And then this is like you take one pixel and you calculate, you take the neighborhood of that pixel and you create a vector. With some transformation, you create a vector. This is called the feature. And once you select those features within 2 images, then you try to with some algorithm, you try to get the correspondence in between these two feature sets. Once you have that algorithm, then it comes to epipolar geometry, which is pure computer vision. It's a very theoretically founded work, and there are good work like 5-point algorithm, 8-point algorithms are there, which can give you a good estimation of the localization information, not the mapping information, but the localization information. So how much the camera has moved, that can be estimated with this theoretical work with only just 5 feature points or 8 feature points. And then after that, once you know the localization estimation, then you can triangulate. You can triangulate and then create the map. But here there is a catch. The catch is with respect to monocular camera or RGB camera, we don't have the scale estimation. So with a simple example, what it can suggest is when you see a movie like a boat is in a movie, there is a scene of let's say the rain is falling with on a boat which is shaking like heavily on the ocean. So this kind of animation is very costly. You cannot create a whole huge boat or yeah, something like that, and you cannot go to the sea to shoot this, but you can do it on your lamp in a tab, and when you zoom the camera, then the scale goes off. So you see that it's actually a boat which is swinging on the ocean, but the scale, you cannot estimate the scale. What is the actual metric scale, that what is the object size, just by seeing from the image. This is a very crude explanation, but good explanation of the scale, which is also shown theoretically that it cannot be estimated. So with just monocular camera or RGB camera, the scale estimation is not there. But when you have a depth camera, then the scale estimation can be done very accurately. Webcam is there, some visual odometry algorithms, good visual odometry algorithms. They're like SVO, SVO2. These are very good. They work very well. So if anybody is interested, they can go into the GitLab and GitHub and download the code and test it. These are very well-known visual odometry algorithms. Right now, the present research work is mostly going on, or for last five years at least, is on sensor fusion. Like, you have the camera, but with the camera, the frame rate is very low, like 30 hertz. So if you are moving very fast, even when you are walking, if you are turning around, then the camera lose. So it can be shown in computer vision that if the camera is having only just a rotation, then theoretically it can be shown that if the camera is having only just a rotation, then it is not possible, if I may say so, it is not possible to estimate the localization information. There are some practical problems and there are some theoretical problems. So here actually IMU helps a lot, and IMU having a very low cost sensor, the frequency is very high. So you can have 100 hertz, you can have also 200 hertz or 150 hertz. So you have quite a lot of data with very high frequency. So you can actually estimate the velocity, you can estimate the acceleration. So the full state of your robot can be actually estimated quite nicely when your car is moving. So if there is an autonomous car and there is a jerk in the road, a very big bumper, then your camera vision is kind of shaky and it gets lost immediately. And once it gets lost, then it's very difficult to remap it with the old map and what to do, all these tricky things, the engineering issues, they're really difficult. So to have a very stable system, you need to have these kind of other sensors which are very fast, but within very short time they are quite good, but you cannot totally rely on them fully. Like I mean, you cannot rely on them for even 1 second. You can rely on it, and you can have these very stable visual odometry or SLAM algorithms with all these two sensors, maybe three sensors. So people are actually working on this particular area, how to do, how to fuse different kind of sensors together, and how to integrate them so that you can have a very stable system. So this is actually a very good work. I have taken this flowchart from Hong Kong University. So it's called the title Visual Inertial State Estimator. There are multiple works in it's called VINS. So it's the pre-integration part is the new concept, and there are earlier algorithms for the sensor fusion like EK filter or Kalman filter, extended Kalman filter or uncentered Kalman filter. There are multiple works in the fusion work, but this is a very good approach, I'd say. But the results are pretty good, and it's quite stable. Yeah, so this is one particular work which is very interesting. The next work which is very interesting within the research community right now is deep learning. And with respect to deep learning, it has to be partly classical and partly deep learning side. It has to be end to end. But the main problem in deep learning is it has to be supervised. So if you train the deep learning model for some particular images, then it is not very scalable to other scenarios. So, and it's not very, the main learning is you do not know where, if something is going wrong, then it's very difficult to point out where it has gone wrong. In classical theory, where you have a very good fundamental theory, mathematical theory, then you kind of know, like in this case in Vein's framework, you exactly know that which block is giving, can give you some problem, and what is the theoretical foundation of that problem and how to tackle that. So there can be a good research with respect to that. But in case of deep learning, you have no such idea on how to do that. So it's very difficult over there. But people are doing great work, and there are very good examples in creating depth from the monocular camera, which is very much good with respect to robotics. Research in there, you can say that people are doing this, and it is one frontier of the future research work. So deep learning is definitely one frontier. The other most important frontier of the future work, future research work, other than sensor fusions, although there are a lot has to be done with respect to sensor fusion work. One particular problem, which is when the scenario is dynamic. There are some classification like not very dynamic, like one person is working in front of the camera and the camera is moving. or one car is moving in front of the car. Sorry. There are other dynamic scenarios like crowd scenarios, like when you are moving in a very crowded road or traffic, or very highly dense traffic, then typically any algorithm so far developed, none of them works very closely. So all the demonstrations that you mostly see for autonomous cars, they are mostly in lonely area. Mostly there is nobody. It's a high road. Only
So
one or
Arniv,
two people
I'll
is
just
working.
like to step in. Sorry to just interrupt.
Yeah,
Please
yeah,
wind up
sure.
in 2 minutes so that we can have we can stick to our timeline. So please wind up in 2 minutes. Thank you.
Yeah. So there are four research topics in here. One is the direction of the dynamic objects and the state estimation of the dynamic objects from the sensor of your use, multiple sensors in some cases. Of course, the ego state estimation, that is the localization of self. And the fourth one is creating the map with not only the static scenario but also the dynamic moving objects. And machine learning problem, the deep neural network problem, I already told you, and there was a very good discussion in CVPR 2018. And this is there is another topic which is research frontier, which most of you are familiar with, which is called event camera. It's a very new camera which came up very recently, and you can actually, it goes up to 1 megahertz frequency. So it's a camera, but the signal is very low. It's not typically monocular or RGB camera. It sends on or off signals. But in neurocomputing or in neurovision, this kind of camera is very good. So yeah, that's it from me. These are the references. Thank you.
Uh, thank you, Dr. Arnab, for the presentation. Nice presentation. Uh, though it was more of text, but the audience definitely will have a feel of what localization is and how the robot does the simultaneous localization and mapping, and what are the challenges involved with tracking and estimation, and your research topic of a new vision-based approach for localization that you presented. So thank you for your nice presentation. I would
Yeah, I
also,
have
yes, hello.
I, I have just one video
Yeah,
which
sure.
we have
Yeah,
done
video is perfect. Like,
TCS.
please go ahead.
So it's a window detection and going inside the window with a drone. With the SLAM algorithms is working, the window has to be detected, and with a lot of wind, there is a control algorithm which is working perfectly. So yeah, this video tells itself.
So this was the experiment done at TCS Innovation Lab in Kolkata itself.
Yeah, yeah. It's actually have done with TCS Bangalore in with collaboration of TCS Bangalore, but this is our algorithm. This is what we have developed in Kolkata,
Okay.
and yeah, this is actually ISC Bangalore Air Force ground, airfield.
So I had experience with Professor Swagat, Dr. Swagat Kumar, who was at Noida. So
Yeah,
yeah,
yeah, he is my classmate. He's my batchmate actually.
okay, sure. So I will be
And
definitely contacting you related to the presentation which you made. I had some doubts, so I will get back to you via email. So again, thank you so much
sure,
for
sure,
your presentation
sure,
and
sure,
time.
sure.
Our next speaker is Dr. Sajid Nisa. He has received his MS and PhD degree from Kyoto University, Japan in 2016 and 19 respectively. Currently, he is a junior associate professor at Kyoto University of Advanced Sciences in Japan. He is the founder and principal investigator of Novel Intelligent System at Advanced Robotics Lab at the University of Kyoto. Sorry, the name is Kyoto University of Advanced Sciences, which focuses on the design and development of robotic system for application in robot-assisted surgery. And as we can see, he has already shared his slides, and the topic is towards haptic-enabled surgical robot and human assistance system. So I will pass on the presentation to Dr. Sajid. Thank you so much for coming and joining with us. Please go ahead. Thank you.
Okay, thank you very much, Dr. Amran. Can you hear me?
Yes, yes, yes. Your voice is clear, and your image is also coming, and your slides are also looking perfect. Perfect.
Okay, thank you very much. And yeah, it's a great pleasure. My heartfelt thanks and congratulations to Dr. Mohan, Dr. Abdullah Amir, and Mr. Sutian for having this nice workshop and webinar and having so many speakers from around the world. So it's going great. So I am already running a little bit short of time and I have many slides. So I will try to keep this presentation not very boring. And for the audience, I would suggest if you have any questions or if you would like to have a chat about something, you can stop me in the middle. Okay, so I will be kind of introducing what I am doing at Kyoto University of Advanced Science. And so before that, I think I should introduce myself. I am a junior associate professor currently with Kyoto University of Advanced Science and a Department of Mechanical and Electrical Systems Engineering. And my research interests are basically human-machine interaction and surgical robotics and haptics. So I would like to mention and thank my collaborators as well, Professor Matsuno from Kyoto University and Professor Ellison from Stanford University. So in today's this short presentation, I will introduce three things. First will be about the surgical manipulators and tools we have been developing, and then wearable haptic exoskeletons, and then haptic-enabled driving assistance systems. So coming directly to the first thing, so maybe some of the audience will be already very familiar with this, but I would like to just go over what is the difference between minimal invasive surgery and the open surgery. So open surgery is we know have been done for centuries, where surgeons just cut the human tissues, skin tissue, and operate inside using tools directly in their hands. But around 1980s, there was a new kind of surgery introduced, which is still done by directly hands using certain kind of tools that are inserted inside the patient body through small holes. So the surgeon will insert tools and as well as one camera, and they would look at this video monitor you can see, and they will see that video output and manipulate the surgical tools inside the patient body. As you can imagine, this surgery will be a lot difficult, but it has many advantages. So some of the advantages are the patient recover quickly, and in the recent times, this kind of surgery is surgeons' preferred alternative wherever possible. So, but doing this kind of surgery is very challenging for surgeons. So they have no sense of touch as compared to the open surgery. They now use tools that are thin and cylindrical, and their tools have inbuilt mechanical advantage. And it's very difficult for surgeons to train themselves to handle these tools carefully. So they spend a lot of time. And even with tools, they have difficulties in holding these tools for a long time. And it is well known that surgeons develop kind of fatigue, muscle fatigue, by doing this kind of surgery regularly. So robots are really a kind of device that fit here well, and we can use robots to do this. But to make robot for doing this kind of surgery, the first thing is to know what kind of surgical motions, what are the kinematic requirements for doing this kind of surgery. Here you can see like different degrees of freedom, like pitch, yaw, and translation, and the rotation of the surgical tool. So one main difference with this surgery and other open surgery is the presence of this small hole, which is the real success of this surgery. So you don't cut other tissues. So you just make a small hole and insert the tool and do the surgery. But doing this for robotic arms is challenging. And some researchers were very clever. And for example, they developed this kind of nice mechanism, which is called double parallelogram mechanism. And this is a very simple mechanism, but it can give you this nice small hole in CN point constraint, we call it. So this constraint is by default provided by this design. So there is no chance of any failure. Even your controller doesn't work or something bad happens, this point will always remain at the center of that hole inside the patient body. So the most famous surgical robot many people would know is the Da Vinci surgical robot, and the manipulator of Da Vinci surgical robot also uses this same mechanism. So what are the problems with this one? And you can call these are the problems of Da Vinci surgical robots as well. But basically, these are the problems of this mechanism design. So there are two issues I would like to highlight here. So one is surgical tool's entry angle and insufficient degrees of the manipulator. So what is the tool entry angle and why it is challenging with, for example, Da Vinci surgical robot? So I am trying to like highlight here. So if we have the surgical tool inserted in the patient in certain port locations, so the desired goal is to keep the surgical tool kind of perpendicular to the surrounding tissues. So the reason for this is that there should be no undue stretch in the human skin tissue. If there will be stretch, then there will be post-operative pain and other issues. So how this problem was solved is not only this is the purpose for this device, but they call it a pre-surgical setup device. You can see like the highlighted portion in the purple color. So this whole device is used to just orient the manipulator. It has other purposes as well, but one of the main purpose of this pre-surgical setup device is to make sure that the entry angle of the surgical tool is within the comfortable range. But otherwise, this has a lot of issues. This is a too big thing to have in the surgical manipulator, and also very cumbersome to move from one place to another. So ideally, we would like to solve this problem by proposing some kind of new improvements in the mechanism of the manipulator so that it does not need this big device to maintain the angle at least. So to do that, we proposed a new mechanism which is also based on similar principle, but it has certain novelties which make the angle between the surgical tool and the skin kind of into the comfortable range. So I would like just to make this presentation a little bit interesting here. Rather than going into technical details, I would like to show what we did. So here you can see like this is the CAD model of that design, and we can do this different degrees of freedom motions with this design, and this has ability to maintain the angle to the patient body without having that pre-surgical setup device. So to test this device, we also designed a surgical tool which has 3 degrees of freedom and can be replaceable. So you can just insert this tool and remove it from the screen, the surgical robot. And this is a master controller device we built to control this robot. So I would like to quickly show here, like you can see the operator is just operating the surgical tool, and we can have all those movements which surgeons would like to execute during the surgery. And we did like some experiments to show this manipulator design can not only maintain the angle, but also can do the basic surgical tasks required to pass for the application in minimal invasive surgeries. So on the right side, you can see that there is like a zigzag path and the operator is moving. So this operator is just a non-trained person and using this robot for the first time. And if you, people familiar with minimal invasive surgery would know, like this is otherwise very difficult to do if you give the minimal invasive surgical tools to do this. So, for example, here the operator is moving peg, this ring from one peg to another peg, and this is just untrained first time. So the coming to the other second limitation of this mechanism called double parallelogram, which is the base of the Da Vinci surgical manipulator. So here you can see like this mechanism can do this motions, but one key motion required for surgery is the translation of the tool coming in and out of the body. So it is not possible to do with this mechanism. So basically, Da Vinci surgical manipulator cannot do that. So how did they solve it? They put some extra actuators on the distal end, on the tip of this manipulator, and execute that translational degree of freedom, which has a lot of disadvantages, and the maintenance of such a system is very difficult. So you may know that the surgical tool of Da Vinci robots cannot be used for more than 10 operations. So we have to discard them. So one of the reasons is that we just actuate them on the tip of the surgical manipulator. So we proposed a kind of new mechanism to solve this. So here you can see like the typical mechanism on the top left is just doing a pitch motion. We call this in one plane. It can move like this. But we proposed another mechanism. Maybe it will be a little bit difficult to visualize, but this mechanism can go up and down. So the translation is achieved through the mechanism itself. So the manipulator based on this design will be able to provide translation by itself rather than using some extra means. So just moving to the second section of my presentation is the wearable haptic exoskeletons. So maybe we know like there are like world grounded devices and body grounded devices. So in world grounded devices, the device is fixed to the environment. For example, this is a Phantom Omni device on the left side, very famous one. And a body grounded device is where the device is not fixed to the environment, rather it is fixed to the body. And for example, here you can see this cyber grasp is a famous haptic glove exoskeleton device. And it applies force on the human hand and can provide different configurations to your fingers, but is grounded against the human hand. So, so in the existing research, there is no study what this different grounding locations would have effect on the device performance and how it will affect the user experience and haptic perception. So in our research, our goal was to identify whether this is possible, it is comfortable, and if there are different grounding locations possible, which grounding location will be better for having better device performance and better user experience. So basically, we are trying to understand what is the relationship between the device performance, user experience, and the grounding location. So here you can see like just an example. For example, if we want to make a haptic device that provides a feedback to your fingertip and gives different configurations to your finger. So we could have 3 grounding locations just as an example. So these blue portions, back of the hand, and this proximal phalanx and this middle phalanx, these could be the grounding locations. So to achieve this, we developed 3 different designs of the wearable exoskeletons. And using these, we can understand what is the relationship between the different grounding locations and the user performance. So here is a just like kind of zoomed in version of the design we proposed. So this device can provide haptic feedback along the finger axis, and it can open and close it. And you can use it for operating a surgical robot, or you can use it for application in virtual reality. And here are like 3 different realized prototypes of this device. And with these prototypes, we used them. This is a like just small video which shows the operation of these different prototypes. So you can see like it can open and close and apply force along the finger axis. So if the user is operating a surgical robot, the user can feel the force and understand the configuration of the forceps of the surgical robot. So this is the second where the grounding location is on the proximal phalanx. So just to skip like this operation of this device, we did like psychophysical experiments to understand user haptic experience and the device performance. And this is just a kind of elaboration of how we did what was the experimental setup. So you can see here the user is wearing the device and interacting with the virtual services using our device. So we measure different metrics to see how good or bad the users were doing. So what we measured was point of subjective equality and just noticeable difference. So it's not important to know what they actually are, but the PSE is just gives you the understanding how accurate the user was understanding the force. For example, if the device was providing 1 Newton force, the user also felt 1 Newton force is PSE. And also the just noticeable difference is kind of the resolution of the device. So which means how small a force user can feel using this device. And then we also had 2 subjective metrics, the realism of haptic device, where we asked the users to rate if they were touching the thing with their own hands or using this device, how much they would feel the difference, and ease of the use and comfort of the device with different grounding locations. So I would like to just quickly go through these results. So this first result shows the accuracy of the haptic perception, which is shown to be best for this proximal phalanx. But I think that will be very difficult in this short presentation for everybody to understand what is this, the meaning of these results. So I would like to just give a summary of what we concluded. So what we concluded was that first thing is like grounding location is very important when you are designing a new device that is wearable and is grounded to the human body. So it is very important to decide where you are grounding. So don't take it just for granted. And the second thing is if you want to increase the task accuracy, then the location of the force application and the grounding should be as close as possible. So if the grounding is close to the fingertip and the point of application is also the fingertip, then you will result in higher task accuracy. But that will result in decreased user comfort. So as is the case with most of these machines, so you have to make a trade-off. And I would just like to move to the third section, which is very interesting one. So I would quickly go through. So here we are developing a haptic-enabled multi-sensory driving assistance system. So what is this driving system? So we have a number of driving situations in our real life. So for example, when we are just tailgating, I mean when you are just approaching the car in front of you and the car is just braking or stopping and you are not familiar with that. And for example, another situation is you have to take a right turn. So in the existing system, navigation systems, you have to look at your navigation system or listen to the audio commands that you have a right turn 300 meters away or something like that. So doing all of this requires you to just shift your focus to something else. Something else means you are driving, this is your main task, but you have to look at the navigation screen or you have to listen and focus on this thing. So this is a kind of distraction. For example, there are pedestrians on the road and you don't know that they are there unless you focus. But if you are using a smartphone or doing something else, you might not be able to notice them in time. Another situation is when you have a speed limit and you are just above the speed limit. So the navigation system will not tell you that. And you have a red light and you are still moving. So what will happen in these situations is the result is we spend a lot of time on the traffic lights because somebody is just not looking at the traffic light very actively, and also a lot of fatal accident occurs due to this, that the driver was not able to notice the traffic light or was not able to notice the pedestrians on the road. So we looked into this, and haptics, which is related to sense of touch, is a very nice technology, and we were not able to see how a haptic can be used to solve this problem. So just briefly mentioning, we came up with a solution that uses haptics and AI to detect and make decisions, and we just provide the drivers haptic cues. So in this case, the driver does not need to take their eyes off the road. So this is a schematic of this
Where we can
system.
improve more.
So you can see like
Interesting.
there is a camera on the dashboard.
Speaker interested you the most, or something like that. What are the key points that you observed from the presentation? What you learned? What topics?
Dr. Amr, so are you talking to me? Okay, I think
Sorry.
in the chat. Yeah. So
Please go ahead.
we have like a haptic cushion here. So the haptic cushion will provide vibrations depending on this driving situation. So this is what is this idea. So you can see, like, for example, here, if the car in front of you will be just making an emergency brake, so you will have this kind of alarm vibrations. And if there are pedestrians on the road and you are moving, so the cushion will just keep different vibration patterns. So this is very vivid, and you don't need to just take your eyes off the road to understand it. And you can see, like, this is just a representation how different directions will be conveyed to the users, that you have to move in this direction or you have to stop or something. So we did like a simulated experiments and also a real world implementation of this system. And here you can see a user is just driving a Unity based simulator, and we are like just recording a lot of data and different information, how the user is just getting the feedback using the haptic system. So for example, if there are pedestrians on the road, the traffic light is red or green, and if you are observing the road speed limit or not. And this is, sorry for just passing through quickly here. So this is a video of the real implementation of the system. So you can see a camera on the dashboard, and we are just doing the live computation on board and detecting cars and pedestrians and giving feedback to the user. So this is just an overview of the system. And these are the results of our user study from the simulator, which in summary is that if we provide haptic feedback, the drivers make less mistakes and they enjoy the overall driving experience, feel more comfortable, and it is also more safer. So that is just a kind of like summary of these results. And if anybody would be interested, I will be very happy to discuss more. So with this, I would like to close, and thank you very much.
Thank you, Dr. Sajid. Thank you for the nice presentation and nicely put content. I really learned a lot from the slides as well. So questions are open from the audience side. Please type your questions and ask quick questions.
I'm sorry, I was not looking at this chat during the talk. So if somebody asks,
if someone can even open his mic and ask, is okay.
Yes.
So from audience, any question, please? I have one question. Can I ask?
Okay, please.
So for the daily operation task, was there any time delay between the master and the slave unit? How you overcome it?
So the limitation of the human perception is 300 millisecond, if I am not wrong. So the human can perceive difference of communication if it is beyond 300 milliseconds. So in our case, because we did this, although this was a teleoperation system, but just in the same location in the same room. So we connected it live, kind of. So the difference was less than, I think, 10 milliseconds.
Okay.
So that was like just doing live thing.
Okay. Yep.
I have a question for Mr. Sajil.
Yes.
Hello. This is Christy from Christ University. The haptic solution you gave for the traffic situation was quite interesting, Mr. Nizar. I would like you to tell us, what sort of challenges were there when you were trying to experiment on the road conditions, On road conditions, you have experimented on this particular device of yours. What were exactly the challenges that you faced? We would like to hear from you.
Okay, yeah, I think that's a very nice question. Thank you very much. So I think this is the case with like most of the AI based solutions. So it depends really on how good the training data you have. So for example, in our case, the neural network, most of the data available for the roads and the traffic lights and other things was not from Japan. So what we did when we tried like the data sets available from, for example, US, so it was not working well. The main reason was the traffic lights in Japan are horizontal, but most of the traffic lights in US are vertical, or even in Europe. So what we did is we kind of like developed our own data set, which was local, and then we trained the neural network for our own data set, which was kind of representative of the images here. So this is like, I think, part of what you asked. So this is like one challenge: how to make sure that your AI system works for all different kind of trends and situations. And in many locations, as you would understand, for example, in countryside or in some portions of world, the road signs and other things will not be very visible. So far, we are not considering those kind of situations. And what we have done is our kind of this product is aimed for urban situations where everything is fine. But the problem is that there are a lot of traffic and a lot of traffic lights, and humans are moving close to the driving area. So this is, I think, a great challenge, and probably as AI is not my kind of specialty, but I think as the deep learning and other technologies are making progress, so we hope to have better results in the future. So thank you very much.
Quite interesting. It is really interesting. Thank you.
Thank you, Dr. Sajid, for such a nice presentation. I would like to now invite our next presenter, Dr. Rajesh Kannan Megalingam. So, he is the Director of Humanitarian Technology Labs and Professor in ECE Department, Amrita Vishwa Vidyapeeth University, Kerala. He completed his master's and PhD at Amrita Vishwa Vidyapeeth University and his bachelor's at Anna University, Chennai. His research area include agricultural robotics, healthcare robotics, robotics for humanitarian application, design for manufacturing and embedded systems. He has published more than 150 research papers at various international conferences, journals, and book chapters. He has won several international awards, including the IEEE Undergraduate Teaching Award 2020. So congratulations. This is this year. The Outstanding Branch Counselor and Advisor Award from IEEE New Jersey, USA. So I would like to welcome Dr. Rajesh Kannan. Please proceed with your presentation. Thank you.
Thank you very much for the introduction. Am I audible?
Yes, and your slides are also visible to us. It's clear.
Okay, good. So there was a good introduction by the host. So I'm the director of the Humanitarian Technology Labs. So today the presentation is going to be about some of the robotic solutions that we have developed in the past few years that are applicable to the COVID situation and the new robots that we built during the past few months after the pandemic breakout. Let us move to the overview. So the basic goal of the lab is to devise robots for the humanitarian cause, particularly in the field of healthcare, agriculture, and disaster management. And in my lab, there are 7 senior researchers, including 5 PhD students and more than 50 undergrad student researchers. One of the unique thing about the lab is we encourage undergraduate research in a very huge way. And you can see that there are more than 140 plus research publications, including journal papers from the undergraduate students. 11 patents are applied so far, and we have already received 1 US patent. And we have so many international and national recognitions. So let us move on to the first robo of today that to be introduced from HutLab is the Self-E, or the self-driving navigational robo. You can easily relate if I use the term self-driving cars. So this is similar to that, except that it is not a car. So it has a powerful LiDAR sensor which can map the environment. Once the map is created, it can be uploaded into an electronic gadget, and with the help of the gadget, you can navigate anywhere in the facility that you mapped. The basic thing is you need to create the map first before using the wheelchair. This has been widely tested in Amrita Institute of Medical Sciences, the medical college of our university, with the stroke patients, all right, and some handicapped patients. So the test outcome were really impressive. And then this pandemic outbreak, this could be one of the possible wheelchairs that could be used. In fact, we are going to supply 12 of these self-driving wheelchairs to the Amrita Institute of Medical Sciences for using with the COVID patients, because there is no need of wheelchair pusher, or there is no need to touch the wheelchair or the patient if the patient can drive to wherever is needed. So I have a short video about this wheelchair also.
The self-driving cars are nowadays trying to make people's lives easier. But the technology can also be extended to wheelchairs for helping the people with mobility issues. The interest came out after investigating the people who depend on wheelchairs and wheelchair pushers to travel from one place to another in an airport. We realized that people with mobility issues face a lot of difficulties in their day-to-day travel, and most of the times have to depend on a second person. Our self-driving wheelchair, Self-E, can change the way the society looks into the wheelchairs. Self-E system has 3 phases. In the first phase, the wheelchair is driven through the environment where it has to operate and creates a map of the environment. A similar map is created in the Android application that we developed, where the user can point to the destination that he or she decides to travel to. Once the destination is pointed through the app, Self-E wheelchair plans the shortest path and moves the wheelchair towards the destination. The hardware equipment we use consists of a single laser scanner. Laser scanner can identify the environment and also moving objects like we do. The onboard software automatically reroutes the path while avoiding any sudden obstacles in its path.
Selfie, the first self-driving wheelchair in India, was developed at Humanitarian Technology Labs, Amritapuri campus, Amrita Vishwavidyapeetham. Selfie was
Maybe I can
possible
skip
due to
this
the
part
constant
because
support
it's already
from our beloved
introduced.
Amma,
So
Our self-driving wheelchair, Selfie, is fully operated using any Android-enabled device like smartphone or a tablet. The users have three different modes to operate Selfie: manual, auto, and fixed modes. The manual mode has easy access to the wheelchair with a simple direction interface where the user has to continuously navigate using the app. The fixed mode is used for navigating common places like shops in airports or rooms in hospitals where the destination is known in advance. In auto mode, the user can choose any destination on the provided map. The user has to just point to the desired location using the Android device and the wheelchair starts moving. Self-E can also navigate through tight spaces like passing through doors, corridors, and even getting into a lift. This autonomous technology can be used to deliver goods in industries, food in restaurants, people in airports, hospitals, at grocery shops, etc.
okay, so we go to the next one. Okay, so the next one is the recently developed robo called Annapurna that can supply food, water, and medicine to the patients in the isolated wards, particularly in the COVID scenario where there are so many patients, those who are isolated. This can be a very helpful robo. So this is already tested again in Amrita Institute of Medical Sciences and also Amrita Kripa Hospital, which is a hospital nearby to our university. This can be remotely operated, and it also comes with a telemedicine facility so that the doctors can remotely interact with each of the patients in the isolation ward. It can be either controlled with the mobile app, or currently we are developing our own customized app for the control using Bluetooth or Wi-Fi communication. And it's also very cheap that we fabricated this. The manufacturing cost only up to rupees 25,000 rupees. So I have a short video about this robo Annapurna. Annapurna is a tele-operated robot developed at Humanitarian Technology Lab, Department of Electronics. So you can see that the robo carries food. There is also a medicine, water. By the operator or the nurse to serve food, drinks, and medicine to the patients in the isolation wards. This way, the nurse or the operator need not come in direct contact with the patients in the isolation wards. This robo can be built and assembled within few weeks, and it comes at a very cheaper rate of less than 25,000 rupees. Okay, so that is about Annapurna. Next, we go to the next one, which is Bodhi. Bodhi is a public surveillance and awareness teleoperated robo. One point I want to mention that the presentation today is more application oriented than research. So because now this is particularly the topic chosen is so application oriented. So I'm not going to the research aspect of some of these projects. So the police and the security personnel, we thought, how could we help them, right? Many robots are being developed for helping with the people at the hospital, including nurses, doctors,
and healthcare workers. But what about the security personnel? For example, Bodhi can be used in a containment area where the roads are shut and the people in the houses are not supposed to come out except for some emergency cases. So this can be very helpful during that situations because even the police cannot enter the street or the security personnel cannot enter the street. So they can send this robo, which is equipped with a 360-degree camera, so they can see and also play recorded instructions to enlighten people about the need to stay inside the homes if they see somebody is roaming outside. And this is also a tele-operated one, but it works on Wi-Fi or WiMAX, and it can operate up to a safe distance of about 500 meters. And depending on various features, the cost is also going to vary up to 1 lakh rupees. Now we move on to the, maybe I will have a short video on this one. Bodhi is a tele-operated robot developed for the benefit of security personnel, can monitor from a control station and operate this robot. So the steering wheel is a wireless control one that can be inside the control room, and this robot can be remotely operated. Cameras. So both the front, back, right and left movement of the people can be monitored, and also there can be an announcement system which can go online in case if the police or security personnel see the people movement. This can also play recorded messages continuously and can move up to a kilometer of up to 1 kilometer in a wireless way. So the next robo is going to be the Prabha, right? So this is also developed recently in the past few months. So this is a ultraviolet disinfectant robo, which can disinfect a room of size 12 feet by 12 feet in less than an hour or 30 minutes, depending upon the power of the light, the tube light that is used in this, or the ultraviolet light that is used in this robo. Again, this is a tele-operated one, and this can be of various versions. It can be switched on remotely because this is an ultraviolet tube, and the radiations can be harmful to human beings. So when it is operated, it has to be isolated. So no human can be present inside the room while this is operated. So what we do is we can leave the robo inside the room and close the room, and it can be switched on remotely. That is one of the features. And when it is switched on, there is a siren that is also enabled so that if any person accidentally enters the room, there can be kind of a warning listening to the siren. And it can be used to disinfect rooms where the COVID patients were staying, or it can also disinfect the restrooms, medical equipments, etc. And it is also very cheap, that we manufactured for about rupees 23,000. So the next one, yeah, there is a short video about this one. So this is a AC operated one. It can also be a battery operated. Prabha is an ultraviolet disinfection and control. This robo has 3 powerful ultraviolet lamps at 55 watts and can disinfect
a room of 12 feet by 12 feet within less than an hour. This also has a upgraded version which can have 6 lamps at 55 watts each lamp and can disinfect the room of 12 feet by 12 feet within less than 30 minutes. Because it's remotely operated, there is no need for the person or the operator to come into direct contact with the ultraviolet radiations, which are harmful to eyes and skin.
So the next one that we are having here, sorry about that.
Which are harmful to
Okay, so the next one is the teleoperated wheelchair. It is what we did was there are already powered wheelchairs. Most of you might have known. The these powered wheelchairs come with the joystick control interface, right? So what we thought during the COVID situation, right, this patients who are really sick cannot operate the joystick by themselves, right? A nurse or an operator is needed, but the nurse or the operator cannot touch the patients or even the wheelchair. So what we do is we had already developed this that we had in the lab, a teleoperated one. So we took this for testing at our university hospital, where the operator can operate this wheelchair at a safe distance of up to 4 meters, and the operator need not touch the wheelchair or the patient. So it can be very useful for these operators in wheelchairs, because when we went and were preparing for the testing, there are about a dozen of wheelchair operators who conveyed to us that they are really scared to transport the patients using the conventional wheelchairs. All right. So even though they are equipped with some kind of protective gear, they still have this fear they express to us. And I think that this can be one of the useful way of transporting the COVID patients in hospitals where they need to perform tests or x-rays. And these are all in different facilities rather than at the near to the isolated wards. So I have a short video of this. So I'll skip this because I already spoke about this.
From isolation for the operator to touch the wheelchair, touch the patients. It works in a Bluetooth wireless interface, and the operator can operate it at a safe distance of more than 1 meter. In this way, there is no need for the operator to come into direct contact with the patients or the wheelchair.
Okay, so the next one is going to be a robo that we are working on for several years. All right, even though this is not related to the COVID situation, right? So this is Amaran, that this unmanned robotic coconut tree climber and harvester. We are working on this for almost 5 years now. All right, and this is a very challenging one because of some of these reasons, where each coconut tree is unique and the robot should work for all the coconut trees in the world. That means there are infinite number of situations that we need to face. And also the robot is not operating on the ground. So that is also another challenge for us. That is, if it's operating on the ground, you can make the robo bigger as you want, and the weight of the robo is not a concern. But while climbing the tree, the weight is of utmost concern for us. This idea that we gave, we started based on our chancellor's, the university chancellor input. There are so many poor people in Kerala, particularly the state where I am from, that has a lot of coconut trees, and there is an acute shortage of human robotic coconut tree climbers. People suffer, even the poor people who have 1 or 2 coconut trees, their entire income depends on these coconuts, but they don't get people to harvest the coconuts at right time. Even the coconut industry is facing an acute shortage of this coconut harvesting and also skilled people. For example, for several millions of coconut trees in Kerala, there are about only 5,000 coconut tree climbers. You have to book the coconut tree climber as early as 3 months in advance in order for you to harvest coconut from your trees. That is the situation. So, as I mentioned, this is a very challenging one. That is why it is continuing for years, but we have not stopped. We have not given up. So this is a very complex system of various moving parts. One is the robo that has to climb the tree, and another one is the harvester that has to position properly in order to cut the coconuts. And one point that I want to mention here is the coconuts are cut in bunches and not one by one. So recently this got into the final round of the Cisco Global Challenge. And I have a link to that video, which will throw some light on how the robo works. I don't know, my mouse pointer is having some problem. Yeah. Hope I am keeping up the time. Maybe in a minute this should be over. Yeah.
There is a huge shortage in coconut tree climbers. This affects the income of the farmers in a huge way. In addition, this leads to the price hike of the coconuts and coconut products, affecting the consumers. In Kerala, there are 180 million coconut trees and 50,000 trained climbers.
Professor Rajesh, your video is not, I think, coming.
Oh, okay.
In reality,
are you able to see the video now?
7,000 trained climbers.
No, we can see you, but
okay. So what happened was, okay, okay. So I think I have to share the screen. I shared only the PPT screen. So let me try to see whether I can share the.
You can first stop share and then again start sharing the whole screen.
Okay. Let me, because WebEx is first time I'm using. I'm not used to WebEx, so.
Yes. No worries.
Yeah.
And good that I think you can, because the presentation seems very interesting. You can slightly extend as well. The next
I think I can finish it. I can give you the link. I can give the link. You can watch the video later. I can share the link in the text window. So okay. I think with that, I will conclude my presentation. And if there are any questions that I can take, right? I think I have exceeded the time limit of 20 to 25 minutes. Hello, can you hear me?
I can hear you, but can you hear me? Hello?
Yeah, I can hear you. Yes.
So audience are open to ask questions. So just very nice and informative development task we can see from Amrita University that is ranging from wheelchairs to even the present COVID situation and coconut cutting tree solution that Amrita University is looking at. Especially, I would like to ask one question: Is so these developments are under some funded projects, or is it like the from university the funds are managed, or there is some collaboration with some industries?
Some of these are funded projects. The main source of funding is IEEE, and some of these are university funded projects. For example, the Coconut Tree Climber is a university funded project of 2 crore rupees.
Audience can ask questions, few questions, just few questions. Then we have a next speaker lined up.
I have something to say, Dr. Rajesh.
Yeah, please. Yeah.
Sir, it was very, very nice listening to your talk.
Thank you, sir.
I could see a people-centric laboratory activity happening at Amrita.
Yes, sir.
Yeah, it's really wonderful. Sir, I have one question. You have this Bodhi you were talking about.
Yes.
It goes into the COVID-infected areas. Now, how do you disinfect the robots?
Yeah. So we need a disinfectant station for that.
Yes.
After the use, as of now, the disinfectant part, even the wheelchairs, if you take after using in the hospital, it has to be taken to the disinfectant station.
Yeah, that's right.
Yeah, so that disinfectant station, that is, we are leaving it to the hospital or we are leaving to the police personnel. As of now, we are not looking. We give some directions on the disinfectant station. We are also giving them the option for using our disinfectant robo, right? But from what we discussed, for particularly the wheelchairs, those are to be used in hospitals, along with the UV disinfectant, they also need some kind of solution or gas-based disinfectant to make sure that it is completely disinfected.
Yeah, I was wondering if you're using a liquid disinfectant. It is circuitry. It's a huge circuitry.
Yes.
The robo. And there are plenty of perforations all around. So I was just wondering, in case you're disinfecting, the liquid disinfectant gets into the circuitry. Have you faced any sort of problems like that?
No. Actually, we have not used the liquid disinfectant yet. We have used only the ultraviolet disinfectant so far. And liquid disinfectant are to be used only on the seats of the wheelchair. They cannot be used on the body.
Okay.
Yeah.
Thank you, sir.
Thank you, sir.
Am I audible?
Yes.
Hello?
Yes.
So thank you, Dr. Rajesh Kannan, for such a nice presentation and introducing us to the robot developed in India. So someone among the speakers were asking why we are not, can we deploy COVID-19 robots? So here is one of the example from Amrita University, which participants can observe developed locally, and they are being deployed as well. So thank you so much. Now I would like to invite Mr. Madhu. So he is a co-founder and director of Oceana Robotics Private Limited. He is also the director of Brightson Electricals, an established company whose principal activity is building and repairing of ships. Yeah, sorry. So, yeah. So he's responsible for the overall management.
I have a question for Mr. Rajesh Kannan, sir.
privately ours or just after the session, we have open space. So after this presentation, you can ask lots of questions to Rajesh, sir.
Sir.
Is it okay?
Is it okay?
Just after the session, you
Just
can
after
ask.
the session, you can ask.
Because we have Abra Chaudhary,
who is not presenting.
So I would like
So I would
request
like request
Dr.
Dr.
Kannan sir
Rajesh Kannan sir
to be available
be
for next 1
available
hour.
for next 1 hour.
Is it okay, sir?
Is it okay, sir? Or
hello?
Hello.
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 Hello. Can you hear me? Hello.
Yes.
Yeah.
Yeah, we are seeing your
slides. Oh, good. Hello, everyone. Hello, everyone. I am Madhukumar. I am CEO of Oceania Robotics, and I am also director in Wrightson Electricals Private Limited. We are operating in Singapore. One second. We are operating in Singapore. We are doing ship repair maintenance services in major shipyards in Singapore, like Keppel, Semcorp, ST Marine, Pax Ocean, Semcorp, etc. Ship repair maintenance industry is not like other industry, pharma, manufacturing, and oil and gas, because those industries is already implement the robots, even automation systems. But this marine industry, the ships from various countries, and they can't easily optimize the robots. It's very challenge on that. And ship repair industry is required high labor skills and quick delivery. Especially for ship repair maintenance industry after ship sail, you know that we cannot connect spares into the middle of the sea because the ship is already sail into the middle of the sea. So it's a very difficult process is currently going on. This ship repair industry to involves various trades like electrical, mechanical, automation, instrumentation, piping, steelworks, information technology, safety and security. So I'm a director in Wrightson Electricals. We already covered almost 90% of jobs for this trades. So we try to build the robots for this industry. Ship repair and maintenance service market, its revenue reached almost $40 billion in 2028. In Singapore ship repair maintenance service market, it's already reached $5.5 billion in 2017. It increased every year. This one is a very big industry. I have been working past 15 years in this marine industry. That industry nature of work is be labor intensive, it's be repetitive process, it's dangerous, it's time consuming, and safety hazards and facing environmental issues. I already tried some robots into these marine applications, but that robots have some limitations. They have limited mobility. Example, for ship hull, they're doing robot cleaning operation is 50 to 60% only. They have limited autonomy because that means they're only doing teleoperator mode. That means each side for 10 robots, they want to be doing 10 teleoperators do the jobs. We will see video in later. And that robot's limited scalability. And they have maintenance issues because that robots are from Europe and the US. So if any fault in the robot, they send back to the own country to repair it. and that robots is be very, very expensive, like 200, 300 US dollars, 1,000 US dollars. So for this gap, I want to build my own robots in Singapore. So I reached out Professor Mohan. He's from SUTD. He will join together. We start a company, Oceania Robotics. It's founded in last year, just 1 year. It's a Singapore-based robotic company for manufacture pioneering autonomous robotic solutions for ship maintenance industry and pest control industries and all other relevant industries. We are co-founder for Oceania Robotics. So Dr. Mohan, she's currently doing assistant professor in SUTD. He's holding department EPD, Engineering Product Development. He already published more than 100 papers in leading journals. And he given support like technical and design to deliver the best robots into Singapore and other part of the world. It's me. I'm already working in many industries. It's surprise. I'm doing manufacturing and marine, logistics, and food and beverages. So my idea want to be, at least one robot for each industry. And that robot want to be connected. Like a marine robot want to be used logistics robot want to be used food, something like that. So our intention want to be make robot for multiple applications. Yeah, our robot is be adaptive. In terms of mechanisms, like our robot is variable applications mode. One robot doing cleaning, even inspection, paint stripping for multiple tasks. Our robot is be variable autonomous mode, even manual mode. For autonomous mode, for one tele operator, they control 4-5 robots to save the manpower and production cost. And our products is be scalable platforms and applications. So that means we want to use robot in marine industry, the same robot we want to use environmental industry. And our business model is not only sell the product, we going to give it to the rent it out. It's be cheaper and more useful for the clients. Yeah, we are 1 year company. So far, its current progress is going on. We're doing high pressure hydroblasting robots, grid blasting, inspection and water jetting robots, even logistics. Here I show some videos for better understanding what's going on shipyard, like a manual and grid blasting process. Know that the people, the blaster, the holding the pressurized, the pressurized is like a copper slacks to hit into the wall. So they remove the paint, of course. They want to be do slow process, and the whole environment is be polluted. And this guy, the holding pressure like 3 to 4 hours continuously with a minimum break. You see that how much polluted. So while this processing, this blasting in ship, they are not allowed for other works. So this process is going to take 2 to 3 days in shipyards. Even that one day the dock in shipyard like 30 to 40,000 US dollars. So the ship, they already spend a lot of money just dock and do the painting. The paint cost is be different and the grid blasting cost is be different. So sometimes they doing 3 to 4 people, like the holding one chamber, continuous jobs. This one hydroblasting, they're going to apply the water, water. This one how much psi? Is be 40,000 psi to remove the paint. So he's holding that much of pressure into the heat into the ship hull to remove of paint. This one for continuous job is one everyday jobs in shipyards. Is currently going on. So the blaster, they have the metal allergies, even the hands and the fingers injuries. This one happen, the frequent time of interval. They're facing a lot of issues for these blasters. So for our idea, for this gap, we're going to replace this blaster. So replace means because the blaster, that one is a heavy work. It's not that much of people is available in the market. So we want to be blaster is your operator. So they're doing robot for a complete operation. So we build a robot for Oceana Robotics and SUTD for to solving these issues. Yeah, our robot. So this robot, you imagine this one did 40,000 psi to hit into the ship hull. So they remove paint, and it's a wide area. It's not like a man doing. Our robot is be autonomous. So we just given the data input like a 5x5, 3x5 meters. So our robots doing that much of cleaning. And for each side, for manual cleaning, they're using 30 to 40 people. But we're using our robots, we minimize up to 10 people, balance all use robots. So this one for effective output and give high quality, and especially in marine industry, time is a very, very important. So we're going to save the time and save the people also. It's a blaster. This robot is a continuous operation, even day and night. We give that much of support, give that much of system involved. I have shown another video. This one we did in Keppel shipyard in rig, in its offshore vessel. So we're doing up to 2,800 bar pressured into the hit into the wall. So we clean the complete cleaning of strip out the paint and whatever dust. This robot process is a ship hull, it's a side hull. You know the sea growth for every vessel, ships on sail on the sea, right? So they have a lot of growth. So once a ship enter into the shipyard, they want to be remove it. So almost 30 to 40 people to involve with this process to strip out this sea growth. So we want to use our robots to clean these all things. I shown for another video. This one for the same robot, they're doing environmental cleaning. So we changed some minimum designs. So in Singapore, especially in Singapore, the labor is the main process. So we use our these robots for all shopping mall, even sports complex, and HDBs, housing development boards. Yeah. So we are already doing for these robots for in R&D. These robots same like previous ship hull robot. So we given given some data for 5x5, 3x5 meters. The robot is helped to clean continuously. So for this process, it's not required so many people, and the effective cleaning in progress. Yeah, shown that much of cleaning process. We have another robot for doing National Environmental Agency. This one is a fall ceiling inspection robot. You know very well our house cleaning vacuum robot. It's a move around hall rooms to clean. The same process for this robot doing fall ceiling. So this robot is move around the fall ceiling to identify the pest, like rodent dropping, cockroach, any other kind of pest. In Singapore, very clean city, so the NEA officer, the pest control companies, they keep on look into every week or monthly, twice. They're doing regular inspection for this robot, especially for inspectors and pest control companies. So this robot is going to move around into the false ceiling to identify any pest like rats movement and other purposes. The pest control officer, they cannot access for all the false ceiling place. So they're using teleoperator. They use our robots to move around into the false ceiling. I simply say false ceiling is not like our ground floor. It's not that much of smooth. They have a lot of wires. It's a very hard access. So we make robots for this false ceiling to up to 80 to 90% to identify the place. So this robots is a very useful, not only false ceiling purpose, for other purpose like food industry. The food industry is required, it's a very clean area in all food stalls and restaurants. So this robot is going to be monitoring purpose as well. So I have for another robot, this is a logistics robot. This logistics robot is a heavy duty one. We're going to use up to 6 tons. This robot is mainly used for large area. They have already in AGV in market, but we're going to do for a heavy duty, like 6 to 10 kg. This one is mainly used for shipyards because the ship once in dock, they have a lot of equipment from one place to another place, like take motors from into the electrical workshop. So we're going to use these robots. It's more useful. This one is R&D level. Of course, it's a AI catchy word. So we are also using AI processor for our robot. Example, our ship hull inspection robot. This robot, we feed the data for good and bad surfaces of the hull. So while the work in progress, they compare the current and old data images to give the best output. So for that purposes, we're going to use AI processor. We implement all the robots for different applications. Cloud structure. We currently using our 4G for all the robots. For next year, we're going to enable 5G as well. For this one, mainly for data transforming and storage purposes. This robot is mainly used for take more data for future R&D purposes as well. This one is our manufacturing capabilities. Want to do all the systems. For this year, we're going to launch a product for hull painting and paint stripping robot. For next year, we're going to launch for logistics and pest control robot. And we're currently doing some other robot R&D. Thank you. If you have any questions, let me know. Hello.
Yes, Kumar. It was very interesting.
Yeah.
We would like.
Sales of this product. You have sold a lot of products. How were you able to market and welcome you get in marketing?
No, we already work with the local shipyards. The Keppel shipyard already given a lot of support. So this robot is ready. We're going to launch in Keppel. So the Keppel is all over the world. So it's easy. So this one support from local shipyards. Yeah.
Very interesting. And what? You were showing the demonstration of the paint.
Sorry,
what would be the pressure of the paint?
Yeah, the pressure is be higher for grid blasting, like 100 bar plus, but hydroblasting is required 40,000 psi to apply the yeah.
So what is
about
100 bar
100 bar
pressure
pressure is required for grid blasting? For
faint blast?
Yeah, the grit, the copper slag to hit into the wall through compressor.
Yeah.
With the compressor. Yeah. Thank you very much.
Dr. Rajesh, are you there? Rajesh also.
Mr. Amir, you are there?
Yes, I am here. Hello.
Okay. Who is coming in next?
No, I mean, okay, one second. Hello. Actually, our next speaker is Abra Chowdhury. Unfortunately, due to some unavoidable reason, he could not join. Hello, am I audible?
Yeah, yes, you are audible. Please go ahead.
Yeah, so I'm just trying to say that Mr. Abra Chaudhary, he is the next speaker, but unfortunately he could not join due to some unavoidable reason. So during this time, maybe we will run over a few of our lab videos, our recent research.
Who was sharing the screen? Can you make me pause?
Okay, I'll just okay. So as the next speaker is not available, we will do some of our recent research works, which is already published for the viewers to watch. Thank you.
Hello.
Angvu, can you hear me?
Yes, please. Yes.
Yes. So you can present your work later. We will be presenting the research activity during your time. So you can continue with the presentation at the moment. Thank you. So just, let me introduce you first. Sorry. So as Dr. Abra was not available because of some reasons, So now I request Dr. Angwu Lee. He is an optoelectronics research group, faculty of electrical and electronics engineering, Ton Duc Hang University, Ho Chi Minh City, Vietnam. Currently, Dr. Lee is working as a postdoctoral research fellow at Road Lab of Singapore University of Technology and Design. He is the Road Lab leader in various aspects of reconfigurable tiling robotics autonomy. He received his BS in electronics and electrical from Dong Duc University, Korea in 2007 and 15 respectively. His current research interests include robotics vision, robot navigation, human detection, reconfigurable tiling robots, feature matching, 3D video processing. So I would like to invite Dr. R. His title is Reconfigurable Tiling Robotics, Feasibility for Deployment. Thank you.
Hello. Can I audible? Yes.
Yes, you are audible, and your screen is also, we can see your screen.
Okay. So, good afternoon, everybody. So, my topic today we will discuss about the reconfigurable tiling robotics, whether it's feasibility for real deployment. The reconfigurable robotics is a recent development and roll up in SUTD, one of the leading research in this field. And so we will focus on several aspects of reconfigurable tiling robotics. Start from the trajectory checking, control power consumption, path planning, some AI algorithm, and also we will also want to validate the trial of the environment. And so you can see here the one of the very popular platform robot. This one is the vendor already claimed they can sell about more than several hundred million units, and then this market very news. And you can see the fixed form had very drawback to access the narrow space, and also don't have any option to shift to another form to overcome the environmental change. So at the reason, reason we move with another solution. We develop the robot that can change shape, and robot is based on the polyforms, and we can somehow to change the polyform to different types. And platform also can attack more blocks and make the platform very flexible. And the outcome of this platform is with two different aspects. The first one we can cover the predefined workspace, and with the tiling theory. The tiling theory is the very well-known theory to generate the tile set to cover the predefined workspace. Given the work figures, and the second aspect we can see here. Here, robot can change its shape, and then we have another option to overcome this situation. This is very unique problem in the cover area coverage. And in our lab, we developed the framework to do coverage to make sure the entire coverage, and then we based on the framework of channel assignment problem to find out the optimal trajectory. With the cost function, consider the robot option, and the robot will generate the shape, and then go to the 3D deploy sequentially, and to cover the whole workspace. And then the next framework we focus on the reinforcement learning. This one we try to simultaneously generate the optimal tile set, and also the minimum number of shape change during cover the space, and the cost function and the reward function of reinforcement learning is based on the real operations and the real energy consumption when the robot operates within the workspace. The work function including the three components: the transformation, the rotation, and the translation. And you can see here on the example robot, the robot will transform into the full shape, the square, the I shape, and the L shape, and the requirement rotation of each block need to be rotated to fulfill this action. With the simulations, you can see the robot will move around the workspace and cover the whole workspace with the minimum number of sections. And we compare the algorithm with the very one popular brick algorithm, and then the platform can generate very less and so the generation time is less than another method. And with the developing platform, we will have the question that how we can apply this theory to make the real robot. And then the robot we develop in the lab is will be range from the teleoperate to the long to the fully autonomous. And we focus on the development platform called Estate Road. Here we integrate the LIDAR, the real and the Unreal, and then to do the sensor fusion. And then the robot up to now we can work almost in the several location. We also integrate the driving training module to similar to mimic simulate the cleaning action in the real-time environment. And we also choose different test beds in our city and also in the outside environments. And you can see here environment is quite complex with a lot of areas that is equal to set, and then the robot will provide real-time localization and also the obstacle avoidance and also can make sure it can go through the under the table and between the chair leg. And then the obstacle is randomly located on environment. And for the long-term autonomy, should we develop our state machines framework, and then to make sure robot can operate by itself, and then with the intervene by the humans. And the robot can firstly the robot to be controlled by the human to view the map, and then the map will be decomposed into several. This section, this progress will be done by the own element. And we also have because we can see the recovery robot, there are several steps. So to integrate the pump sensor similar with the normal robot is quite difficulty. And then we have another method to detect the obstacle, like we use the LIDAR to detect the obstacle, and also we use the current sensor to detect the obstacle. If the robot collide with obstacle, will be the spark in the current, and then we detect this event, and then find out the obstacle location during the route navigation. And then another challenge with we focus on it how we can do the trajectory tracking, because the robot has the several blocks, and then each block will have the different locomotion, individual locomotion, and then the synchronize between the each locomotion with the quite challenge with the reconstruction robot. And we develop our own PID control. And this PID control will do the loop back, the close loop back, and then to synchronize the four blocks together and generate the velocity command, and to drive robot to keep to follow the global plan. And here we show the video to demonstrate the operation of robot. You can see here robot with the four blocks, and then each block is one of the different fly locomotion, and then the robot is operate in autonomous mode, and then you can see it can do the single zigzag environment, and then it can recover to the previous location to reach to the 100% coverage, and then with the disturbance from the environment, the robot can still move in the predefined, the predefined trajectory. You can see here, these are some end-to-end. You can still cover the trajectory. You can use the dynamic obstacle, this problem, here the video we show our trial at our frontier, the small workspace, and in the bigger workspace. The trial conduct within more than 2 months, and then the robot operate for about 1 hour every day in different shifts and in the different operation, the autonomy mode, and to make sure the robot can cover the whole area, as much as possible, the testing environment. And during the trial, we record all the data, including the number of trials succeed or failing, and also the number of mechanical issues. And based on the data, we tune and apply the modify to enhance the platform and enhance the operation of the platform. And you can see the robot can have to overcome very several difficulty. The robot is have to go into the middle of the chair, transform the shape to different one, and also have to overcome the obstacle. The platform is operating autonomously and without any intervention by the humans. You can see here some situations the robot has to detect the very thin chair leg and then go in the between, and without any bump sensor and another physical sensor. It's only based on the LIDAR and the current sensor to detect the obstacle. The robot is low, and then it defines the landmark, and then it finishes the 2D5 plan, and then cover the row by row. Here, the video demonstrates the efficiency of the robot to the reconfigure robot in terms of area coverage. You can see here the robot that define what is the best set to cover this role. In this case, robot try to make a smaller shape rather than the high shape, the longer one. And because the row space is narrow than another one. So here we also record the error coverage, and then we do the benchmarking with the circular robot. We can see here the error coverage of our platform can achieve about more than 95%. On the other hand, the circular robot, the very commercial one, it only can achieve about more than 80%. And during the trial, we can see that we have the two phase. The first phase in the small space, and we record the number of total error coverage, the successful reconfiguration, the total successful detection select, and also the percentage of accept narrow space within a select. And with this data, we can improve our platform. So as we may know, the reconfigure robot is a very very interesting topics. But the question will be raised whether this platform is feasible for real application. And then during this project and during this trial, we somehow to want to prove that the platform is feasible for real application. The future requirement, we keep testing on the particular workspace, and even we cooperate with the NDI, the Singapore National for Environment, to do the trial at the food court, the public food court. We integrate this platform with this framework with another polyform body platform. We improve the autonomy navigation, and then so we considering the adaptive control in another cluster environment. This now finish my presentation. Any question? Hello? Hello?
Yes. Hello. Audience can ask a question. They can type in, and Dr. Angu will be replying.
So one of the questions is the autonomy framework detail. So for the autonomy framework, actually we can slide, and then you can see that how we going to actually select. The first, we need to build a map, and then based on the map, the algorithm have to apply to decomposition the map into the several section, which is best for the robot shape, and then based on the each section, the robot will be will go around and then define the landmark. The landmark is the location where the robot need to be changed the shape, and what is the best strategy cover our region. And here basically we will have the two factory. First one we will go with the zigzag cover, and then secondly we will go with the fishbone cover, and then mm, every time robot go around, we will detect the obstacle and define the error. The robot need to be covered, and the error robot already covered, and we compare with the map. And the error is the already covered. The robot will be go to the next landmark, and if the area is not covered, we will go back the area again and go back based on the current location and go back to the location again. You wanna?
Any other questions? So I have one question for Angu. Can you hear?
Yes, please.
Yes. Um, so for autonomy of these styling robots, what are the sensors that you are using it for the localization? And as it is a challenging task to navigate between the chairs, especially the thin chair legs, how you are managed to detect those chair legs and navigate in between them for enhancing the area coverage.
So for the sensors, because as I mentioned, quite a challenge when we deploy the bump sensor to detect the obstacle at the normal robot, and then that's why in this platform we LIDAR and the laser information, and then the current sensor to detect the obstacle and to detect the width between the chair leg to detect the nearest point at our robot, and then evaluate the obstacle based on our learning algorithm. And this is only to add if for the don't want to go to so much detail about this, but basically we using some learning algorithm from the LIDAR sensor, laser sensor.
Thank you so much. Any other question? Because still we have 5 minutes. Uh, if anyone has question, then they can ask. Feel free. Now you can open your mic and then can ask directly to Dr. Anand. I think you can show that, Angu, you can share that video of S-Tetro, that where the robot is accessing the narrow passages between the chairs and uh, cleaning the. Are you there, Angu?
Yeah.
Thank you. So this is about the tiling robots that were developed at SUTD, and the autonomy of these self-reconfigurable robots are taken care by Dr. Anguli. If any further questions, you can contact him on his email. He has several publications. You can type his name and then the concerned publication. You can refer and then ask the questions. I would like to introduce my next presenter. Thank you, Dr. Angu, for the nice presentation. Now I will ask Dr. Douglas Wild Wildblue Bettrell from University de Santa Catarina, Brazil. He is currently an assistant professor with the Department of Electrical Engineering uh, at the State University of Santa Catarina in Brazil. He received his PhD and MSc degree from Federal University of Santa Catarina, Brazil. He obtained his bachelor's degree in computer science from the State University in Brazil. His research interests are in applied robotics with an emphasis on robust control of dynamic system, machine learning, and path planning. His goal is to bring robot closer to human life in doing robots with usability feature and autonomous motion skills through a combination of control and computing techniques. Now I like to invite again Dr. Professor Douglas Weilberg-Bertold to present his topic. Thank you. So, yes.
Okay, I think you aren't listening me, all right? So,
Yes,
hello
you are
everyone.
audible and your slides are also visible.
Yes, I'm trying to yes, my video. Here's my video. Thank you so much, Amir, for the introduction. So, as Amir said, my name is Douglas Berto. I'm a researcher in applied robotics, and my goal is to deliver robotic solutions to people without they need to know what a control algorithm is and what kind of artificial intelligence technique or even the number of the sensors or the control algorithm that is used or implemented in the robot. So with this short presentation today, I'm gonna show you how advanced control techniques can make robot more usable and human-friendly. So I'm gonna talk about advanced control. Okay. So first of all, I want to present me and my institution. I'm an assistant professor at a public university here in Brazil. So I teach robotics, artificial intelligence, and industrial automation. And I work with the system automation robotic group, working mainly in planning and control of mobile robots. So although this is a short presentation, we have some agenda. I have some agenda for you. So well, I'll show you a problem. So what I'm looking for to answer, and some concepts about advanced control. So how you apply advanced control in robotics, and how you can apply that to mobile robots. So let's start with that. So this is a common picture. You see here a human and all the robots in the industry. So most of the robotics solution a little while ago was for industry, as anyone knows. So them was always set up by a skilled technician using some specific level of programming in an structured environment. So now we have robots at home in an unstructured environment and used by humans that wants to at most push a button or less and don't want to spend hours or money to make that robot to do what they was bought to do. So now we need to evolve this robot, and evolve the software architecture. And during the next minutes, I'll show you how advanced control can make part of it. So what's our problem? You see here in the display, you see a new robot, the UR robot. It's a new new industrial robot, so the collaborative robot. But the way you program these robots are old-fashioned. So you can program these robots as point-to-point, and this old-fashioned programming, it's not enough today. So here you have two kind of robots, two new thinking robots. They are not new. This robot has almost 10 years. They was released back in 2012. So they are not new robots. But the thing that the way that you program these robots is different. These robots aren't programmed by point to point. So this Baxter and Sawyer, they can learn a task. So they learn how to do a thing. So they don't learn the point-to-point movement. They don't learn the movement. They learn the things that you have to put something inside the box. So they learn this movement, this kind of task. So anywhere is the thing that you want to put in the box. The robot to pick that that thing it put in the box. Anywhere that thing is, okay? So the way that you program these robots is evolving. So this kind of evolution has to be mirrored for home robots. So you can say that robots at home is a new idea. So as you can see in this video, this is Miss and Mrs. 2000 back in 1968. So this is the first robot, industrial robot, the Unimate robot, and Mrs. and Mrs. 2000 are having the meal. So you can see that the idea or the wish to have a robot at home, it's not new. So we have already the machines, but you have to evolve the software. But okay, I show you the industry robots, the industry robot at home. But what we have today to bot? Okay, what I can bot? What's the last thing that we see at a customer can buy? So here you can see a 2020 robot, the Stretch, released back to almost 8, 9, 10 days ago. So a Google guy developed this robot, this Sketch robot, to do things. And this is the best you can buy today to develop. If you go to eBay, you can go buy one of these robots. But this robot is not fully autonomous. They have the button for you to push, but they don't have the autonomousness, all the autonomous things. They are teleoperated mainly. So I bring you this video because one of the main advantage or one thing that this video shows you is the navigation problem. Has to be specific or don't guarantee that the robot will do something most like the human, or considering evolution like a human do, like you do every day. So this is our problem. How can we give the robot something that it's more friendly for human and more usable? So I have to tell you about before now I have to think of I have to show you some concepts of advanced control. So advanced control back to industry is in the industry you have a process, and this process most of time has a closed loop, as you already know who worked with control. So you give a reference, this reference is sketched for a control, and control a plant and give a feedback, okay? But in industry, you have a lot of control loops, and an engineer has to set these control loops, and it's a lot of references. So the references are levels, or temperature, or things like that. But the engineer has to understand that every reference, every parameters are optimized against some high-level parameters like timing, like logistics, or money, energy. So all these high-level parameters has to be optimize it. So you have to set low-level parameters to catch some high-level parameters. So how the engineer can measure or manage all these parameters or translate high-level parameters to low-level parameters. So here, the advanced control can be placed between low-level and high-level. So you have the supervisor. So the supervisor talk about money. So talk about money, about time, about what sells most. And low-level control wants to know about reference, what level I have to maintain, what temperature I have to work. So this is low level, is supervisor level. So here advanced control is allocated. So this kind of control can optimize every parameter of low level accordingly, time, money, logistics, energy, and what else the supervisor can understand. So advanced control work as a translator, almost as a translator. So we have some techniques from industry, mainly chemistry industry. This kind of controls was mostly advanced regulatory control, advanced process control. The MPC, or the model predictive control, is some intelligent control techniques. So how we can apply this idea to robotics? So in robotics, you can think robotics as an industry too, as a process. So you have the process. If you are talking about mobile robots, the process to move or to do some task. So you have sensors and actuators. As industry, you have low-level control as velocity control, position control, and the planning, that is the path that you want to do. So we have the planning with navigation, mapping, cognition. You have to stay safe. All is in the planning. So you have it low level with servo control, trajectory control, stabilization, all this. So between these two guys that thought differently and are aiming these its own objectives, you can place some guy called advanced control. So this guy can optimize energy, efficiency, restrictions. It's the main things that middle layer control can do. So what one of the techniques that you can do, and I work at my research, is with model predictive control. Sorry. So the model, the MPC, does prediction of the future behavior of system based in a model, as the name says. So you give some prediction horizon and control inputs, and you select the best control input to do a movement based in this model. So as the optimization, you can do these optimization based in environment restrictions, actuator restrictions, safety conditions, what is needed for a robot working with humans or collaborating with humans. But this kind of control has a problem. Two main problems is you are in the industry, you have slow dynamics. Process, the control of a process is about minutes or hours. So when you talk about robotics, you are talking about fast dynamics. So with fast dynamics, we work in nanoseconds, picoseconds. So you have not sometimes you don't have enough time to find the right or the control input that you want. You have time to compute the control output. So so MPC is computationally heavy. You don't have enough time to compute the output. So you have to evolve these softwares to work with robotics. This is the main difficulty of using MPC. So what we do here back in Brazil, we still working to do these things, this kind of techniques to work with robots. So I'll show you some videos now that we are doing. We started with this MPC, one specific techniques that is called explicit MPC. So in this video, you can see a simulation of UAV doing a trajectory tracking. So trajectory tracking is not advanced control. This is low-level control. So the first thing we do is apply these techniques to low-level control. So here we see you see low-level control applied to fast dynamics using real-time and ROS. So from these we evolved to real world. So in real world we apply this to a wheeled robot doing the same trajectory tracking problem. So, but now with real world. So you have a low-level control, trajectory tracking, and fast dynamic system with real-time running ROS. So what's the difference here? So the difference mainly the real world. Why we don't do that with UAV? Because a UAV can fall. So the wheeled robot can't fall. At most, the robot can find a wall in his path. So this is the second advanced. So now what we are doing? We are doing some efforts with this guy. We work with people from IIT in Italy, working with quadrupedal in this kind of task, the self-writing task. So a robot, sometimes he can fall in the ground. So to get back in his knees, he has to do some kind of movement to get back in self-writing. So this step is to make the MPC work as advanced control. So here you can see the closed loop proposal. So you have a quadrupedal with a low-level control in his joints, working with position of joints or torque in joints. So you have the planning part, that the same, the planning specify the points that you go. If you remember this video that I show you, so you have the points between the path. So in here, you have a proposal reference governor control. So this RGC is a control that translates the planning to the low-level control, considering some restrictions. So here you can see simulation. We are in simulation phase. So next we'll translate this for ROS and the HiQ platform, and we'll do that in practice. So here you can see the robot getting up. So you have here, we have self-writing problem are doing with system, with fast dynamics, with high abstraction, okay, and advanced control in architecture showing advanced control. So advanced control here can do the step up or the self-writing problem is solved considering some restrictions in the environment and restrictions of the behavior of the robot. So all these, what I show you, is back to YouTube or the GitHub, always open source. and we are working, as I said, with ROS and EMPS implementation. So as I said to you, I think this is here in Brazil, it's 7:20, so 20 minutes. Thanks everyone. I'm open for questions. Let's see the questions.
So thank you, Dr. Douglas, for the nice presentation.
Thank you.
We invite few questions from the audience. They can feel free to type, even open their mic and then ask.
Hi, Dr. Douglas. There's a nice presentation, so thank you very much. I'm Madan Mohan. I would like to ask one thing, is that that RGC, what you have shown, and self-writing capability. Can you explain a bit more, because it will be better, we can understand more. This is an interesting application you have seen.
Yes, I can tell you more about. So what I show you, we have a lot of information, so I have to explain really earlier more. I know. So RGC is not our proposal. RGC is used in other solutions, but not for the problem of self-writing. So self-writing is when a robot or a quadruped, or you can do it with a wheeled robot too. But when the robot falls on the ground, so you have a problem that the robot has to do some movements to get back in his knees, so he get up as we do. So when you fall at the ground, you have to put the dust away and get up. So you have to do some movement. So this movement has some restrictions. So you don't have only your foot on the ground. You have another points of contact. So the high-level control and the high-level sensor and the high-level observer can send you some references of where you have to go to get up. So, but between your actual from your position now to the reference position, so the goal position, the high-level system of control don't know what to do. The system only knows where you have to go. So you have to translate this point, so the reference point, back to low-level joint positions and some considering some torque restrictions and some movement positions. So movement restrictions. So the MPC, the RGC, the reference governor, can select this trajectory, so a smooth trajectory between 2 points, considering all these restrictions. But you are not restricted to torque positions, torque limits, or positions limits. You can select other things, like a robot can be have a restriction of velocity of movement, or restrictions of money. You don't want to spend enough, or don't want to spend the battery. You don't want to be like a robot. You want the robot to do smooth movement, so to be more usable, or it's more user-friendly or human-friendly. So all these parameters aren't joint parameters. They are translated to joint parameters. So the RGC architecture and the advanced control solution do that. So you can use this architecture to translate these high-level parameters to low-level parameters.
Thank you, Dr. Douglas. I just have another one question.
Okay.
Basically, for deciding the reference position for the low-level manipulators or low-level actuators, are you solving any optimization problem using MPC, or you are doing something else to get the reference?
I worked with MPC in the industry for another problem, that is distribution of, or if you have a co-generation system with, for example, from generation from sunlight, or generation from some thermal energy, you can pick the best solution for the time to do optimization as for money. So you can use MPC for this kind of thing. So in robotics, we are trying to do this visualization, because the problem is that you don't have enough time to do the computational problem of using this kind of MPC to low-level control or middle-level control.
Thank you. Thank you for clarifying my doubt.
Thank you for your question. So I think we have time for another question. We have here the participants. What do you think about the accuracy of Islam for mobile robots in dynamic industry environments? So if you think industry, you have an environment that is all, it's easy environment. So Islam, or if you use a fuse of Islam with sensors that are lower, that costs low. So Islam is a combination of a lot of sensors and techniques. So Islam, it's not its accuracy is as good as you want. So for industry, it's easy to use. So it's sometimes for industry, as you can see, historical things, you can use only line in the ground. You can solve the problem, but with Islam, you are using a high-level solution to do things that are easy to solve. Nowadays, man, you're okay? Nowadays.
Thank you, Dr. Douglas, for your nice presentation.
Thank you, Amir.
We have our next speaker with us, Mr. Yokesh Krishnaswamy Tamil Selvam. He's from University of Western Ontario, Canada. He's an active researcher in the field of machine learning and its application into multiple domains, glass facade detection, crack detection. So he's an active researcher in the developing algorithms related to machine learning. I would like to invite Yokesh Krishnaswamy Tamil Selvam to share his screen and start his presentation, please. Yes, Yokesh, you can hear me?
Yeah, I can hear you.
Yeah, now you can share your screen.
Can you see?
Yes, we can see now. It's clear. So I think you can introduce yourself and the university as well. I don't have a
I have very short introduction about you, so you can introduce yourself
Yeah.
as well first.
Okay. So I'm Yokesh. I'm basically working in right now. I'm working in medical robotics, but I have been working in robotics and machine learning for the last 4 or 5 years. So I'm currently pursuing my PhD in University of Western Ontario, Canada. And so today I'm going to talk about one of the use case. So that is my introduction. So I'm now going into the presentation. Today I'm going to talk about one of the use case of the robotic platform and how. Hello. Can you hear me?
Yes, yes. Please go ahead.
Okay. So today I'm going to talk about one of the use case of robotic platform and how machine learning can be used in conjunction with a robotic platform to improve the performance of robots in real world scenario, right? So today I'm going to talk about a cleaning robot equipped with machine learning algorithms to detect any cracks in the glass exteriors. So first, let us look at the research motivation. The motivation of the research is to uh, improve the performance and efficiency at which we can clean glass exteriors of tall buildings. So, as the slide shows, that a survey says that there are about 80,000 multi-story buildings that have more than 12 floors, and each of those buildings out of that 30% of those buildings have glass facades, as in glass exteriors, glass windows, or glass doors. We need to clean all of these glass exteriors, but cleaning all of them manually would be highly time consuming and dangerous. For instance, in one of the tallest building in the world, Burj Khalifa, has about 24,000 glass exteriors. So it takes about 3 to 4 months for the cleaning crew to completely clean all of those glass exteriors just for once. So we need a solution for this, and it's also dangerous. There are a lot of accidents that happen during the cleaning process of glass exteriors when it comes to tall buildings, right? Uh, and human lives could be a danger. So we need a much more efficient method to clean these glass exteriors, and we need it to be less time consuming, and we need it to be less dangerous. That is the whole idea of the project. So the objective is to develop a robotic platform that can clean buildings, tall rise buildings, the glass exteriors of tall rise buildings, which means we want the robot to climb vertical structures, right? So that is the challenge here. We need to build a robot without any ropes involved. We need to build a robot that can automatically climb glass exteriors without any human interaction. So, and auxiliary objective is to make the robot automated. We don't want any human interaction. We don't want a human to tell the robot where to clean and when to clean. We want the robot to detect specific areas to clean and then automatically clean those areas without any human interaction. Because teleoperating a robot is highly complicated and it could be time consuming. So we want the robot to be automated. So that is where the machine learning comes in. So first, let us look at the robotic platform, and then we'll look at the machine learning platform separately, and then we'll see how we can combine them to make it perform better. This is a robot that we're talking about. The name of the robot is Mantis. So I was actually working on this robot when I was in SUTD. When I was working in a project with SUTD. So on the right, you can see 3 different systems. All these 3 systems are involved in this Mantis robot operation. There are 3 systems: a vacuum system, a locomotion system, and a lifting system. So we'll talk about each of the system in detail, and then we'll move into the machine learning algorithm. So these 3 systems are mechanical systems. The vacuum system is to make sure that robot does not fall off the building. You know, we don't want the robot to fall off the building. We want it to stick itself to the glass exterior so that it can clean um, the glass exteriors, right? And we don't want to use any ropes because that is again complicated. We don't want we don't want to use any ropes to make sure that the robot is stuck to the building. So we use a vacuum system. So the vacuum system consists of a suction mechanism. We use kind of a mechanical impeller to stick the robot onto the glass exteriors. So that is the purpose of the vacuum system. Now the locomotion system is pretty straightforward. The locomotion system is to move the robot within a specific window. You know, once it's on a specific window or or a door, it will move itself across the window, right? So the locomotion system has the robot has wheels and it's driven by DC motor, and it will just move up and down the windows. Now the lifting system is a bit more complicated. The locomotion system is to move the robot within a specific window. The lifting system is to move the robot from one window to the next window. For instance, if it has to cross an obstacle, the lifting system will lift the robot and then move to the next window or make it cross an obstacle. So that is the purpose of the lifting system. Now the lifting system is driven by a motor driver and actuator. And these three systems are driven by a microcontroller unit, and it's powered by a converter. In addition to this, we also have an onboard camera which can capture live videos. So this video will then be used. I'll talk more about how we use this live video to build a machine learning model. But for now, the robot is controlled by a human through Wi-Fi and through a laptop or PC. That is how the robot is controlled for now. So what is the need for machine learning algorithm in that robot? So like I said, we want the robot to be automated. We want the robot to automatically detect any spots that needs to be cleaned. There are various aspects to it. The problem is we can't build one single machine learning model to make the robot entirely automated. We need to solve one problem at a time. So in this study, the problem that we tried to solve was to detect any cracks in the robot, any cracks in the glass. So if there's a crack in the glass, we don't want the robot to clean that specific spot, because if there's a crack in the spot, that area is already weak, and if the robot applies pressure onto that specific area, it might break the glass. So we don't want the robot to apply any pressure. We don't want the robot to clean glass surfaces that are already cracked. So that is the problem. We want the robot to automatically detect any cracks. And in terms of the solution, we built a machine learning model using TensorFlow. We built a convolutional neural network to detect any cracks, to build a machine learning, to build an image classification algorithm to detect any cracks and let the robot know that there is a crack and don't clean that specific part of the window. So before I jump into the architecture of the machine learning model, let me talk about how we do a communication system. The communication is based on master-slave communication. So we want the machine learning model to tell the robot which areas to clean, right? So the TensorFlow is the platform for the machine learning model. There are two platforms here: the robotic platform, the machine learning platform. The robotic platform is the robot operating system. The machine learning platform is the TensorFlow. So we want the machine learning platform to tell the robotic platform, ROS, to clean the specific part. So the machine learning platform is a master, the robotic platform is a slave. So we use a master-slave communication to communicate between the robotic platform and the machine learning platform. So the robotic platform, the slave platform, as in the robotic platform which is under the slave, includes all of its system: the lifting, locomotion system, the vacuum system. And in terms of the machine learning platform, we have the model that we created, machine learning model, and we include that model into the master system. So the model is based on TensorFlow. This is architecture. This architecture is a very preliminary architecture. So the architecture is pretty shallow. It's not that deep. We only have like 2 convolutional layers and 2 max pooling layers. The reason is we at this present time we are only detecting if there's a crack in the glass or not. Right? We're not trying to detect the exact spot of the glass in this algorithm. So we are only detecting if there's a crack in the glass or not. So the structure, the architecture of the model is pretty shallow, as in like it's not that deep. So in this architecture, we use 2 convolutional layer because it can extract any deep features, any high level features, and we need high level features when it comes to image classification. And we use 2 max pooling layers to reduce the complexity of the operation. So as you can see, the input is the image, as in we get the live video from the robot, and then we separate it frame by frame, and then we convert it into images, and the output is the cracked and uncracked output. So we find out whether a specific image is cracked or not, and then the robot will act accordingly. So this is the basis of the convolutional architecture. So when it comes to the results, we use 2 different optimizers. Optimizers are really important in terms of understanding how to get to the global maximum, and it's really important in terms of converging to the global maximum. So we need to choose the right optimizers, and therefore we tested it out with 3 or 4 optimizers. I have only stated 2 optimizers here. So in this, if you look at the accuracy or the F1 score, which is what we usually look in terms of detecting the quality of the optimizers and the quality of algorithms, the Adam optimizers F1 score has been is pretty high compared to adequate. So we decided to go with the Adam optimizer, and that is what we used in terms of finally implementing it in the robot. So I'm going to show you the working of the robot, and then we'll look at how the machine learning model works and how it can be integrated in terms of improving the performance of the robot. So on the left, you can see the actual robot. On the right, you can see the spots the robot has cleaned. So the bottom image shows the onboard camera. Okay, so that is the working of the robot. Now we look at the working of the machine learning model. So this is the video from the onboard camera. So and based on the video, we'll get the probability of crack and uncrack will change. Right now there is no crack in the glass, and we're getting the correct output as uncracked. And the uncracked probability is about 92-99%. It's on the up. It's at the top of the image. And now there's a clear crack in the image, in the glass, and therefore we are getting the output as cracked, and the crack probability is about 99%. So the accuracy is pretty good. So we use this algorithm, and then we connect it to the master-slave communication, and then we, instead of operating it through a laptop or PC, the aim is to at some point use this algorithm and communicate the output to the robot, and then let the robot know that there is a crack in the glass, and not to clean that specific spot. So these are some of the references that you can look at. First, if you're interested in knowing more about the machine learning model, you can look at the first reference, and if you're interested in looking more at the design and construction of the robot, then you can look at the second reference. Thank you. Thank you.
Thank you, Yokesh, for the nice presentation. We now ask audience to put their questions with Yokesh. One can open their mic and ask questions. I can.
Mr. Yokesh, I have a question.
Yep.
This is Christy from Christ University.
Hi.
The Burj Khalifa building, was there cleaning carried out, or did you carry out cleaning using your model on any of the high-story buildings?
I'm sorry, you asking me if we actually if we integrated it in the robot at this point?
Yes, yes.
So we actually got the data. Actually, this was a project that was done like 8-9 months ago. So we got the video from the robot and we trained the model. But in terms of connecting it to the master slave communication, we did the connection, but we haven't made it completely automated. The robot is not completely automated at this point. Like I said, the automation, there's a lot of steps in terms of automation. Detecting the cracks. So detecting the cracks is just one step, because there are a lot of aspects in terms of making it more automated. So it's we need more machine learning models in terms of making it more automated. So no, we haven't.
You explained the brain part. You have explained the brain part of it.
Yeah, exactly.
But just out of curiosity, how do they do the cleaning in Burj Khalifa? Do they employ any robots at the moment?
Well, certain parts of the cleaning in Burj Khalifa, actually Burj Khalifa is an example that I gave, but in most of the tall rise buildings, this is what happens. At very high areas, they use a crane to either clean it, or they take people to clean it, or in certain low areas, as in like the certain lower floors, they actually use people on ropes. I think there's an image that shows that in my slide.
The first slide that you showed, right?
So there are some people cleaning it. So
they were just
exactly. So so there are still people cleaning it. I mean, it's not. They're not using robots, but I think I think we're moving towards that at some point.
Yes. Okay. Thank you. It was very nice listening to your lecture. Yes.
Thank you.
Hi, Yogesh. Can you hear me? Okay. Yeah. So I saw it's a very nice presentation. Thank you for your effort and dedication. Okay. So of course, this is an facade cleaning robots for very multi-story, especially very high building. Okay. So what are the safety aspects included in the robot itself? Okay, the means it will not, if there is it will find any cracks. That is for building aspects. My question is, what are the safety aspects included in the design of robot itself, in the safety of robots? Because it is moving in the very tall building on the external areas, in the windows and all. So what are the safety aspects designed into the system for robots?
In terms of safety aspects, right now we have a vacuum system that can help the robot hang on to the wall, as in like it uses suction system to keep itself attached to the wall. So that is a safety. That means that suction system is pretty powerful. We use an impeller to make itself stick. So that is a safety aspect. I mean, we don't have any other safety aspect at this point. We just use a vacuum system to make itself stick to the glass exteriors and hope it doesn't fall.
Okay, so something like some kind of, it will be adhering to the glass by some suction.
Exactly.
So it also is there any how much pressure the adhesion, the force, because some glasses may be high thick, some may be thin. We don't know building to building or manufacturer of the glass depends upon the manufacturer. The thickness strength may be different. So
You're
based on
right.
the thickness of the glass, whether the robot know what suction pressure should apply, because if the glass
No,
is
at this point it
slightly
applies
low
one
strength.
constant. At this point it applies one constant pressure. But that is actually a very good point. You're right, because the thickness of the glass changes from building, not just from building to building, even from window to window. So that is a good way to change the pressure, the force at which you can change the suction pressure. And we can use this. So if we can collect the data from the thickness of the glass, we can build a machine learning model again to make it even more automated. But at this point, it applies a constant pressure.
Oh, okay, I understand. So this will be the next your future work, based on the strength of the glass. The suction pressure may be very. It can understand. It
That is
can
one of
detect
the
it
aspects
very.
that we can. That is one of the aspects that we can look into making it, making the robot even more automated.
Okay, understand. Okay, thank you.
Thank you. Thanks for the question.
Yes, Yokesh. I have a question. I am Amir, again from SUTD. So, with the machine learning and especially the crack detection, I think the effect of lighting on the glass is also an important aspect. Like, because if the light will fall, if the sun shines on the glass, it glazes, right? So that will also come as error model, something like that.
Exactly, you're
So
right.
your
You're
detection
talking
algorithm, how
about
much
building a
accurate is
machine
in
learning
that
model, right?
condition?
No, I'm sorry. You're talking about building a machine learning model. You're talking about the training images. I didn't understand your question.
So yes, if you change the lighting conditions, the performance of detection of the crack will vary, right? So how much is the
you're right.
accuracy
So,
under different lighting condition? Basically, it's outside, indoor, or with a constant lux. Basically, lux is the unit for the light intensity.
Yeah.
So depending upon the
So
lux, how is the performance?
in terms of training, we used images under different illumination. That is what we used. We took the training data, taking this into consideration. That the illumination, the amount of light that is falling onto the glass might change from time to time, right? So we need to make sure it can adapt itself. So we use in terms of collecting the training image. The person who collected the training image, she collected data under different lighting conditions. I mean, so we took that into consideration, and when we built that machine learning model, we did collect training data from different lighting conditions, and thereby it will compensate for that. Hello. Hello.
Yeah. Hello.
Can you hear me?
Yeah. Yes. Sorry, my mic was off. Yeah. So thank you for answering the question. And
I think there is one more question that is on the screen.
Yeah, sure. You please go ahead.
Yeah. So can we use the same ML technique in underground design for crack or internal defects? Yeah, you can definitely use it, but I'm guessing what Amit said about illumination will come into play. When it comes to underground terrain, it is going to be a bit more dark, so you need to adapt. Adapt your model depending on that. But you can definitely use ML techniques to detect any cracks and internal defects. So it's basically a trial and error method. So you need to try different models like I said, this model is a pretty shallow model. So if you want to make the model complicated, I would advise adding more CNN layers and adding a regularization to make it to not overfit the model. So that is what I would advise. But you can definitely use this technique to build a crack detection model to detect any cracks in the underground line. All right, thank you.
Any other question? We still have 5 minutes.
Yeah. So I think there's a couple of questions on the screen.
Yeah, please go ahead.
LiDAR point cloud. Can you elaborate on what do you mean by LiDAR point cloud? Because I have not. You're talking about LiDAR sensors. If you're talking about LiDAR sensors, I think can detect. I think your question is, can we use LiDAR sensors instead of using an image? Can we use LiDAR sensors to detect any cracks using a machine learning model? You can definitely use LiDAR. LiDAR is, I think, to detect to detect a distance. So I'm not sure how you would get sufficient data, informative data from the LiDAR that can point out to a crack. But you can, if the data that you collect is informative, that can actually suggest that to build a machine learning model and detect any cracks. But in terms of LiDAR, I think LiDAR can only detect the distance. And you can definitely use that. You can definitely use the LiDAR sensor to detect any cracks using the machine learning model. Okay. All right. Any more questions? Hello. All right. Do you have any more questions?
Is there any other question from audience?
Sir, sir, can I raise question?
Yep, go on.
Sir, actually, in your architecture, you have kept 2 convolutional layers.
Yeah.
What is role of a second convolutional layer, sir?
So the convolutional layers are basically to extract high-level features. The convolution kind of separates the image, like divides the image and then start extracting high-level features. The more convolutional layers you add, the more deep features, the more high-level features you get. So, but you need to be careful about not adding too many convolutional layers, because if you add too many convolutional layers, then you might overfit your model. So the additional convolutional layers are to extract even more high-level features. So that is the point of convolutional layers, adding an extra convolutional layer. But you need to be careful about not adding too many convolutional layers.
Okay, sir. Okay. That it will extract features from max pool layer, sir.
No, it will. Oh, you mean that you're talking about that specific layer, the second layer?
Yes, sir. Because
so
the input came from max pool layer for first convolution layer. Then the input for second convolutional layer will be given by this result from max pool layer, no, sir. First max pool layer.
Yeah. So the input for convolutional layer 2 will be given from the max pooling layer 1. We add max pooling layer to reduce the complexity, to reduce the size of the image, size of the data, and then the output of that max pooling layer will be given to the convolutional layer for further extraction of features.
Thank you, sir.
Thank you. All right. I think we're done with the questions.
Yes, thank you, Yokesh, for the presentation on detection of cracks using machine learning approach.
Thank you.
It was a nice session. Now we have our next esteemed speaker. His name is Professor Subir Kumar Saha from Indian Institute of Technology, Delhi. Though no introduction is required for him, but still he is a researcher, and in 1983 he did his graduation from RE College of Engineering, Durgapur, and MTech from IIT Kharagpur, and PhD from McGill University. Apart from teaching, Professor Saha is enthusiastic about researching in rural problems, converting rural problems into research topics, which he propagates through a lecture series called Mudra, or Multi-Body Dynamics for Rural Application. He has delivered more than 65 times the lecture on the same in the same area. So he is enthusiastic about putting the robotics into the application in rural areas and uplifting the conditions of the rural people in India. Professor Saha occupied several administrative positions at IIT Delhi. He was the head of the Department of Mechanical Engineering from 2015 to 18, vice chairman of GATE, JAM, GMAT examination during 2008 to 9. So I would like to invite Professor S.K. Saha to share his presentation with us. Thank you, sir.
Hello.
Yes, sir. Your voice is audible and we can see your screen.
Okay, so thank you, Amir, and thank you, organizers, for inviting me for this webinars lectures. And so I put the title little unconventional, the robotics rural, and I think Amir has made a case to tell that okay, what is my interest area, no? So let's see what is robotics and what is rural I'm talking about. So let us watch some video. Okay, for the sake of time, I'm not showing the full demonstration of this robot, which has been tested during the COVID situation in a hospital in Haryana. And this is a robot which is commercialized by a company who is our ex-student, company name is PR Robotics. And this robot has evolved from a student group of our robotics club who have been participating in a competition RoboCon, and I explained that participating in a good robotic competition may give you all the necessary ingredients what you need in an industry. So I call them as industry ready. Talking about rural, let's watch this video briefly. So improvement in batasa making process. Batasa we know in India, we eat a lot, particularly as a prasadam, in temples. However, the batasa, the way it is made, I did not know till I got into this project. It is a collaborative project with one of our ex-students who is a professor in a college. So you can watch how the unhygienic way the batasa is made, and then for the person who makes it, this is very hot, and then the sitting posture is not comfortable. So we need to do something for such people. And so question of product design certainly comes into the picture. And then this was the first layer of conceptual design, which has been tested. Then later on, of course, a modified design has been proposed, and this has been tested in the field. So what I wanted to also show you in behind, you can see that how the environment is. So as in technology people know, if we can do the improvement of the environment by introducing technology, which is not expensive, but at the same time the best in the world, kind of, And here is the difference when you do the robotics research for those people, whether it's a government or it's a multinational companies. Now, money is not a limit there actually. But when you do things for the sectors, grassroots sector, you have to be bounded by both sides, no? So I consider these kind of problems are more challenging than working in plain robotics where money is not a limit at all. So I consider this as a lecture series, and I've been doing it for last several years. And I emphasize these 2 points. The first point is a report in Economic Times, which says the general quality of Indian engineering graduates are very poor because they are not able to fit themselves in the job market. Now, it is not my statement; it is a statement. And if you have the access to the internet, and now you can just check it in Google that what it says. Unemployability of Indian engineering graduates. On the other hand, when you do the research, even in IITs, we talk about very high-end research, but what is its application to the society? It's a big question mark. It's a statement by Swami Vivekananda long years ago. The education which does not help the common mass of people to equip themselves for the struggle for life, which does not bring out character of strength, is it what? So these two are my driving factor to decide what kind of research I want to do. So one is the skilling our graduates so that they become suitable for industries. Of course, research is automatically outcome of that thing. And the second one is, of course, how it benefits the society. So this is one activity of our robotics laboratory, which is sponsored by Bhabha Atomic Research Center. So 2010 to 16, now we have worked on several aspects of robotics here. I wanted to show you two videos of our activity. So this is a video from the contribution of our computer science faculty and students. Let's watch it for about a minute. So operator wearing a glass, and basically we wanted to control a real robot using this Omni Phantom, and this is a virtual robot. Now the screen basically is being controlled by this person, and then the signal goes to this place remotely, where Amir must have worked during that time also. So this is immersive environment. Is a contribution from our computer science department professor. The idea is we don't use the video feedback. This is a real robot. You can see the distance in one corner of the room, and the guy is not really watching this robot. Let me stop here because you got the idea of what immersive environment we are talking about. Next one is adaptive force control. Here we are trying to insert the peg in a hole using the force torque sensor. So you can see Amir here while he was doing PhD. So he made this robot compliant. Means this is the need of the day. We talk about cobots actually. So we made one of the industrial robots as a cobot, and at the same time you can see two robots, so we could make them as a teleoperated robot also. So these are the fun learning activities in our laboratory, and this is the part I was talking about. This is a mechanical engineering contribution here. So how insertion. This is fairly a large peg, but we have gone up to 14 millimeter size peg as well, with a clearance of 0.1, so successfully implemented, and a complete set of technologies which is done for BRC and been transferred there actually. So this is what is called the blind search method using the force torque sensors, and finally successfully implemented it. Here I wanted to give this information for the benefit of the researchers worldwide. I know there are a lot of foreign participants in this webinar as well.
This is a company here. I have foundation for robotics. This company is not a profit-making company. This is called Section 8 company, non-profit, owned by IIT Delhi. Basically, it is a technology innovation hub at IIT Delhi for robotics, collaborative robotics, supported by DST in India. And there in this site, I have some brief information for those who wanted to be, collaborator in whatever sense. If you go to this website, you will have some idea about it. So DST will spend up to 150 plus crores, which is about $20 million roughly. And then we have 50 faculty from IIT Delhi and 50 plus, from India, abroad, which includes Japan, Korea, US, Canada, and others. So it's a 5 years program, So please, and our objective is the product. DST wants more product should come out from these hubs. As general philosophy tells us, being in India, even though our body is Indian, our citizenship Indian, passport is Indian, but generally when it comes to products, be it a book to be followed in our universities, we prefer foreign books. At home, we prefer foreign products, same with the robots. I wanted to give you a little glimpse of, in India, good attempts being made. It is only we Indians have to support, and our friends around the world, have to support in whatever way is possible. Be it a research, be it buying the product, testing it, and so on and so forth. So the first one is our homegrown thing from IIT Delhi. The first robot you have seen in the COVID situation. So this is being tested at our laboratory. Please allow me to do fast forward for the sake of time. So you see, when he was pushing, he was not really pushing. He was just showing his intent of pushing it, and the battery, the motor power were on, and it was going. So these kind of robots, obviously, where human and robot are working together. So this is one very nice example of collaborative robotics as we have seen. There are robots by Indian companies like Grey Orange. It's quite famous worldwide. Warehousing automation, Milagro, which makes this kind of floor cleaning robot, window cleaning robot. Adverb is another company for last 6 years. They are doing on mobile robotics. Defense sector, DRDO has created what is called Dux robot and the Netra. There are several companies in the country, at least one I can mention about our campus, the Botlab Dynamics, and one in Chennai. Originally carburetor company, but now they are also making into the aerospace. They make drones. Talking about industrial robots, they are not so successful, but still, surviving for this one for the last 25 years, and this is for 10 years now. MTAB in Chennai, and then Bravo Automation. Earlier, it used to call Tata Automation. Talking about other Systematics is trying to parallel architecture robot like a SCARA type robot, and then there are CIR, KR Bangalore has made the working robot, and then this is underwater by Simon development. And I've been watching during the COVID time, there are at least 10 to 20 different companies who came forward in the airports. They are distributing the masks, and then COVID scenarios, they are taking it to the in a hospital beds. As far as my approach towards skilling part concerned, innovative teaching I call it. Let's watch this video for a while. Let me fast forward. Let me stop. So what I was trying to demonstrate here is it's actually a competition organized by Doordarshan in India. It's called DD Robocon, and this is a video from last year, DD Robocon 2019 held at IIT Delhi. So I am quite fond of this one because the first video or the peer robotics video has actually evolved from one of these competition robots. And here the game plans are out about 8 months before, and so that people have to conceive, design, fabricate, debug, and then finally compete in the scene here. That way, all aspects of industrial scenarios are embedded in one shot. So 2008 Robocon robot we have tested for reliability and robustness for several years. So we have a project called RoboMuse in order to take forward the product from the competition towards the commercial level, and then several iterations 8 to 19, so it took 11 years, and then it's a peer robotics, one of our ex-students took this one. Coming to a little bit on the COVID scenario, obviously, during the COVID, our robotics research in India has gone really multifold. And what we got involved in recent times, for last 2 months, we have been discussing with AIMS Delhi, and then Adverb, that company came forward to help with the arm. They have one arm, and Glimon Research, another startup company. So basically, you would like to develop a tele-ultrasonography, robot during the COVID. So we would like to use a master system like this, and slave will be the arm, and this is kind of scenario taken from one of the literature. So what we would like to do is we would like.
You can open your mic and ask questions, or you can type in as well.
Thank you, Amit, for giving that opportunity. Yes.
Good evening, Professor Saha.
Good evening.
Sir, I have followed your work as an ex-student from IIT Delhi, and I would like to start by thanking you for this inspiring presentation.
Thank you.
What's your name?
What's your name?
I am a student of Professor Kar. My name is Madan Mohan Raiko. I have technical questions, but as your presentation is so inspiring, I want to ask you a more general question, because I feel that a lot of things has to be done, like you said. How far you think India has to go before we can use the robots or autonomous robots in farming? I mean, basic tasks like robots going into the farm and doing sowing seeds and cutting, reaping the rice plants, like that. So how far we are from those tasks if we can use autonomous robots to do those tasks, and what are the bottlenecks that is stopping us from doing that?
Well, question is interesting, but I would go answering the following manner. Number one, how much we need? That is the first question I should ask. Because if US is doing, Europe is doing, we have to do it. I don't agree with that. And just like if I give you pizza bringing from America, you will not like it. But if I bring the pizza from our Pizza Hut, you will like it. It's customizing. So first thing is, if we think we need it, certainly we should use it. But if we can borrow it and then use it, it will not work. If the tractors, it has not been happening. Even John Deere kind of companies from US, they have modified their tractor sizes. So that is the first thing. Once we need it, we could have done yesterday also. It's just our willpower to do it. That's why I introduced the Indian robot, because we as the Indian team, we are not strong at doing it. And that is the first pillar itself. And I would put it that way. We have companies from US, they have modified it, that is -1 day. So that is the first thing. With that thing, now, if you can do it, you have done it start today, tomorrow we do it. I had one example for you. I asked mobile robot company just last week, what is the growth of robotics in India? And then so far, last 2 months,
questions, then I would like to another speaker. So if there are questions from any audience, they can ask.
Here on the chat, maybe if you allow, I can read and then answer.
Sure, sir.
Yeah, the robot for underground drainage management.
So any just one more quick question. I would like to another speaker.
This is difficult problem, but already there is a company in Bangalore who has already implemented here on the chat for the purpose. How complicated scenario you can do it, I am just really sure. But any problem given to me, I would not adopt the way the Singapore is solving or US is solving it. But I would like to cut down to my style and do it. Obviously, some of the components we have to collaborate with other companies around the world and then do it. If you just bring it because things are not so standard in our country, because our habits are such, good or bad, it's a debatable issue, right? So if you wanted to do the way it is not happening in other countries, it may not happen because the standards might not have been followed properly. So the pavement height may not be as uniform as demanded by the law. So it has to adopt that kind of value.
Thank you, Professor Saha. Thank you for enlightening us. I would like to invite my next speaker, Dr. Acosta Calderon Carlos Antonio. He is from Singapore Polytechnic. He just give me a second. Yeah. So he has an extensive background of developing and implementing robotic projects in the areas of autonomous navigation robot, mobile robots, humanoid robotics, human-robot interaction, and smart factory technologies. He is also an effective communicator with excellent planning, organizational, and negotiation strength, as well as the ability to lead consensus, establish goals, and attain results. So I would like to share the presentation role to Dr. Acosta Calderon. Can you hear us, Dr. Acosta?
Yes, thank you.
Yeah,
Thanks.
please go ahead. Thank you.
Thank you. Can you see the screen now?
Yes, we can see the screen, and your voice is also audible. Please go ahead. Thank you.
Okay, thank you. All right, so I'm going to be talking about some of the robotic projects that my students at the Singapore Polytechnic do. And first, I just want to start with a small introduction of what is the Singapore Polytechnic. It's the first polytechnic established in Singapore, and it currently holds more than 18,000 full-time and part-time students. It offers more than 50 diplomas, and it has 9 technology and innovation centers that focus on R&D as well as industrial collaboration. Many of the work is actually done on autonomous mobile robots as well as industrial applications within Singapore. We have, of course, also some extensive work done on humanoid robots, mainly for competition-wise. Then we have also service robots and intelligent systems. And we have extensive collaboration with many universities, local and overseas. Now, as I mentioned, I'm going to be talking about some of the work of my students. Majority of the work of these students is being based on what is service robots. So the main thing of why service robots is important is because we want to find develop applications as well as robotic systems that are able to help with improving the quality of life, especially for people that have certain disabilities or certain constraints and they are not able to deal life by themselves, like the elderly, the handicapped, or maybe the sick people. And why we want to improve on this situation? It's mainly because the population, not only in Singapore but worldwide, is having some issues, because now we have there's going to be a huge gap between the elderly and the very young people. And that gap is going to be an issue, because now you're going to have people that need to enter into the economic force, and they need to start working to maintain the economy and to keep the countries to move on forward. But at the same time, you're going to have, that elderly people, they also need to take care. So who's going to take care of these elderly people? So you need to have probably caretakers or nurses or somebody else maybe helping take care of elderly people, handicapped people, and sick people. And the first thing we try to do is to try to develop service robots to help with some simple tasks. And from there, we try to improve into developing certain applications that are more focused onto specific fields. So why service robots? Well, service robots, or in this case, we're going to be talking more about what is personal robots. So as you guys can see on the graph there, we have what is industrial robots. And the industrial robots, they usually work on an environment that is highly structured, but the level of autonomy is very low. So that means the level of they taking decisions or acting on changes on the environment are very, very low. And as well as you guys can see in the graph on the right side, we have the level of human-robot interaction, and that is also very, very low. Most of the industrial robots, they actually just perform their task. Once you press the button, they are performing the task, and the human-robot interaction is really just the pressing of a button to start or stop. Then you also have, of course, the semi-structure, where you have a lot of service robots. But personal robots, they need to work in more loosely environments, because they need to work in places that might be changing every day, like households, offices, hospitals, and so on and so forth. And their level of autonomy needs to be high, because we don't expect the humans to be taking care of these robots so much. They need to be able to be independent, take decisions, as well as to fulfill the task. And so they might also need to have a human-robot interaction more than another ones, because they're going to be also interacting in environments where humans are going to be by default. Now, one of the things that we have noticed with these personal robots and service robots is the telepresence. Telepresence is a good application, especially if you are going to be creating a robot that's going to be moving in certain environments. You might want it to have the presence of a human at certain environments, at some of those environments. In those cases, the telepresence would be a good feature to have in these robots. I'm going to show you some of these applications where we can have telepresence, and we have been conducting some of the experiments with telepresence. Right now, we're also partnering with Syntel. Syntel is the telco in here, so they provide network for communication, and they are providing now what is the 5G. So now with this 5G, the speed of data is very high, and then we are looking at how we can combine with telepresence. So this is some of the things that we are going to be discussing. So I'm going to be discussing some of these applications. So the first one is about the robot companion.
After this, we have only one more.
As we can see there, a robot companion is a special kind of service robot that is designed for personal use at home. So the idea of a companion is really to be there every day of the life, helping in the quality of life, and helping also with some tasks that the people may need to perform daily. Yes. The first thing I'm going to be showing, the first project is this one, which is robotic pets But it's not like other robotic pets that you have seen. If you attended the presentation this morning, another one of my colleagues talks about a robot dog pet that it can be used for therapy and rehabilitation. This one is a little bit different. This is a soft toy that it has been transformed into a robotic pet. And it's not going to be moving around the house or it's going to be walking, but it has another purpose. Now I want to share with you this video of my students. And in there, they're going to be describing what is the use of this pet robot. Okay, so what you guys observe there in that particular project is this particular pet is to change the emotional state of the elderly people or people that is suffering with dementia there. So I think it's very important because sometimes people just feel lonely. So it's not only the elderly people, but also a lot of working adults are now under a lot of stress. And this robotic pet, it helps on reducing their anxiety and their stress by just simply hugging the pet and patting the pet, and because it actually behaves like a normal pet. But the other thing that we have done, and we are actually conducting some studies, is the telepresence, so that they actually, the caretakers can actually connect through the pet with the patient. It could be an elderly or could be somebody that is actually a bit sad or whatever things in there. And then they can actually interact with the patient. So the other thing that we have from this pet is that we can also measure the level of interaction of the people through the sensors and send this data to the caretakers or to the doctors or nurses, so that they can actually see what is happening to the pet, and from there we can estimate how much is the interaction of the patient with the pet, and therefore the caretakers can estimate if the patient is recovering, is feeling lonely, or is maybe having some other emotional issues there, and then they can take some actions. So the idea of also having this is because having maybe one caretaker will be able to monitor different patients, because the patients are all using this pet. Of course, this project started in 2014, and so far we've been developing the project. We've been developing low-cost prototypes of this project. Probably will go into the market in 1 or 2 years. But at this moment, we just added into there several features so that it can be more convenient for the people that's going to be using this. There is another project that we have that is called the receptionist robot. This is just the torso. As we can see, it's a robotic torso, but it's a anthropomorphic robotic torso. Does not have legs in there. And the idea of this robot is to serve as a receptionist. And why we wanted to have this robot? Well, the main purpose is to provide the receptionist. It could be in hospitals, could be in libraries, could be in places where people need to arrive and register, and put the receptionist robot there. The idea is not to replace the actual receptionist, but to give the flexibility to the receptionist to do some other tasks. Why? Because we have seen, by example, in hospitals that sometimes people arrive, they ask the receptionist for certain things, and the receptionist need to guide the people to another locations. So, or to just go into the next room to pick up some things to give to those people. In the meantime, we can have this receptionist robot to do simple interactions with the other patients or the other people that is waiting in the reception. And these interactions can actually put, like nowadays, when you go into a website, you have the chatbots. The chatbots just pop up in there, and the most frequently asked questions you can ask to a chatbot. So the same thing goes to the receptionist robot. We've been testing now to put the most common questions into the receptionist robot so that people can arrive and interact with the robot. But how does interaction happen? Because of course it's not just like having a tablet there and start selecting questions. So one of the first things is how to have the interaction with the other people. We put the array of LEDs on the face so that the robot can actually produce different expressions in there. But we also mounted a Kinect-like camera on the torso of the robot, so it's able to detect a point cloud of what is in front of the robot, and therefore it's also able to extract information of, by example, human frames. If we can identify human frames in front of the robot, and how close or how far these humans are actually from the robot. Then we can also use with the camera, we use face recognition system. The face recognition system in the together with the frame of the Kinect coming from the point cloud, we use it to recognize if the people is actually facing the robot or it's moving away from the robot, or when the robot is interacting with them, when there is already an established connection. So if the people shifted to one side, the robot will also move the torso following the person that is holding the conversation with, so it feels more natural for us. And there are also, of course, microphones on the door in the Kinect, so that we are also able to detect the sound that is addressed to the robot in there. The robot having two hands. These hands are very simple. At this moment, they are only able to close and open, but we are working on making improvements of these hands so that the hands will be able to actually just maybe point, or maybe have a little bit more of dexterity there. The other thing that we have done is, of course, once we want to have the telepresence of this robot, because we are thinking as well, what if you have, by example, few receptionists, few places, and then there is a question that comes to the robot that the robot is not able to solve. In that case, maybe the robot can actually call to the receptionist in a mobile phone app, and the receptionist from the mobile phone app will do a telepresence to the robot. So when it does the telepresence with the robot, can actually interact with the person that is in the counter there, arriving, asking for information. And one of the things that we wanted to do is to, of course, have the facial expression of the receptionist on the robot, not only to hear the voice, but also to have the facial expressions in there. So, and then we capture the face from the user, in this case, from the actual receptionist, and we combine it with the tone of voice, and we pass it into system where we have this, and the screen that shows the face, the happy face, as the robot moves, the screen is presented in there. And the LEDs are also good indicators for the humans about the different activities of the robot. You'll see later when I show the video. One of the things that this robot has is navigation. So we need to ensure that the navigation safety is very, very important. We needed to have, of course, the safety when it moves around the objects. And by example, when it maps these places like the office, like this one, the office is actually changing. It's not always the same. So the map can be updated by the robot itself. But the map also, we put symbolic names for different places of interest, so that we tell the robot, go to the kitchen, or go to the desk number 1, or go to see the director, and so on and so forth, instead of simply just saying, go to the position 300 and 200 in Y, so something like that. So the other thing that we did is that by using the map, we can actually constrain places where we don't want the robot to move. In this particular office that you are observing there, just behind the robot, there is a glass door. Now, the only sensor that we were having on that robot when we did this test, it was only the LiDAR. And then the LiDAR was giving us problems because of the glass door and because of the light coming from there. So we actually constrained our map so that it doesn't have to go and it doesn't have to look at these things when it moves around there. So now we're also trying to put some other sensors in there, like ultrasonic sensors, so it has a different performance in there. And of course, when detects users or humans around, it will reduce his speed to be something that is comfortable for humans. These speeds we usually find out through different experiments and surveys that we performed before with other robots, with other service robots. We identified that certain speeds human is comfortable, especially when it's moving into a corridor. A robot that moves very fast, people will feel very threatened and will move to a side. But we don't want to bother people with these things. So we simply want to have the robot and the human interacting in the same location. Sorry, let me show you the video now. Oh, sorry, well, I don't know what happened to the video, so I will show you the video for the Sora. And one of the things that we want to do with Sora is we want to change the docking. In the video, we show the robot docking, but the docking for the self-charging has some issues. It still has some problems. It's about 70% to 70 to 75% the success rate for the docking and the charging, but we did another docking when we have developed a method for a flexible for another type of service robots. And so we want to have this docking implemented in Sora. So we're going to put it in there. And from these robots, we have also developed some other robotic applications. And you can see here some other type of service robots. The first one is a robot that we have for exhibitions. The second one is a service robot where it's a general grade there. We can actually mount things. And for that one, we use OmniWheel drive. And then we have also from the same type of Sora, but now is actually for tray return in the campus there. So the robots are actually performing in there. So almost on time. So actually, sorry, I'm eating a lot of time. So I'm going to stop here. So there is a lot of things to do, of course, for our robots in there. And of course, I'll be happy to take any questions that you guys have. And if it's not now, maybe I can answer your questions later. If you can drop me an email, and then I'll be glad to reply to you. Please, any questions?
Thank you, Dr. Costa, for your nice presentation. We would quickly take one question from the audience. So please ask questions from the audience, one question. You can open your mic and ask.
I have a question here. Fahad says.
Yes, please. Yes.
Yeah, are you using ROS for the operating system or something else?
Thank you for the question. So the question is, are we using ROS for the robot operative system for these projects? For some of the projects, the answer is yes. So for For the last project that you observed there, Sora, yes, we are using the ROS, the Robot Operating System. For the first project that you observed there in the presentation, which is the pet robot, we are not using ROS because it's too small, but we are actually just, you're basically just using Arduino inside. It has one Arduino, and we have also a Raspberry Pi inside. So we are using that one. We are using these two things inside, and we write our own small system for that one. For the robot receptionist, we are not using ROS. However, we tried ROS before, so it is actually possible to use ROS on that one. But at this moment, in that robot, we are not using ROS because we feel that, of course, ROS is quite powerful and flexible, but it does not give us a lot of advantages with the current system. Because that robot we've been developing for about maybe almost 6 years right now. So we didn't see much value when we started with ROS, but we did try. We did try the control of the arms and the motion with the ROS before. It is actually possible to do that as well with the ROS. So for most of our mobile robots, we use ROS.
Thank you, Doctor, for the interesting presentation and the demonstration. Thank you.
Thank you so much. Thank you.
Thank you, Dr. Costa, for the presentation. Thank you so much. So we have our next speaker with us. His name is Dr. Shunsuke Nansai. He received his MS and PhD degree in electrical from Tokyo Denki University in 2013 and 15. He was a research fellow at SUTD, Industrial Infrastructure Innovation Center, from 2016 to 2017. He is currently an assistant professor at Department of Advanced Machinery Engineering, School of Engineering, Tokyo Denki University. His main research topics are control theory, robotics, and mechatronics. He has published over 30 papers in reputed journals and conferences. He has been an active member of IDC Logopon, member of the Robotics Society of Japan as well. So the presentation is now up to Professor Shunsuke Nansai.
Hello, can you hear me? Is it okay for that?
Yes, we can hear you, and your screen is also visible with some patches.
I cannot share nothing.
Yeah, you're audible. Please go ahead.
Okay, thank you. Okay, let me start. Thank you, Mr. Chairman. I am Shunsuke Nansai from Tokyo Denki University. Today I will talk about how to develop the cluster-free robot system. So in recent decade, some unique facade highlights building has been built. And it's showing these two figures and other Burj Khalifa in UAE. It's very unique facade. However, even in such new Hangul highlights building, the facade are generally cleaned by the humans. So this poses high degree of risk of fall. For example, the gondola has become suspended in midair at 240 meters height. In another instance, the gondola has been uncontrollable due to the gas window mid-air at 488 meters height. And in addition, every year, some people have passed away due to the falling down during the cleaning. So that situation should be improved by robotics. So to overcome such issue, effort of researchers has been reported, showing these pictures. They show the good result with their experimental result. However, these robots have targeted a specific building, or the robot require particular equipment such as a crane and gondola. That means we need to develop a lot of robots for each building, or we need to build a new buildings which have some equipment only for the specific robot. Of course, that is not appropriate. So our ultimate goal is to develop a glass facade cleaning robot capable of adapting any high-rise buildings. Reconfigurable modular robot system is one potent solution to realize such high adaptability. To realize adaptive glass facade cleaning robot by reconfigurable modular robot system, these topics has been solved. In this presentation, these four topics are focused on, and propose a modular robot strategy and implement a modular robot. To achieve this, following issue addressed. First one is to discuss main requirement for the glass facade cleaning robot and to introduce the modular robot strategy. Regarding for discussion of main requirements, there are two main issues. One is cleaning adaptability, and another is cleaning ability. With respect to cleaning adaptability, the robot has to move, adapting different shape of frames. See, this is the example. One is horizontal long and vertical long, and parallelogram, trapezoidal, and curvilinear. So it seems a lot of patterns of that. There are a lot of patterns about different window shape. However, we can categorize the different characteristics. One is a window size and window shape, and we can say almost glasses. We can say the combination of these two characteristics. Sometimes, for example, the horizontally long parallelogram or vertically long trapezoidal. However, we cannot say, of course, horizontal long, vertical long. We cannot say, but we can say that a combination of these two different characteristics. And another requirement is the robot must overcome the obstacles such as window frame in vertical situation. For this issue, our team proposed the reconfigurable modular robot approach consists of 5 prototype modular robot and its modular robot system. Issue of window size is solved by changing the number of modules. For example, if it's big, wide window, we use 3 and one more module. And if it's close small window, we can change the number of modules to, for example, the 1 module. And for the window shape, we can we design the control system for each module along to the window frame. So sometimes, for example, we control the foot location from here to here, then we can adapt to the shape of the window. And with respect to cleaning ability, scrubber and squeegee are tools which are expert use, as shown in this movie. By simplifying the expert works, there are 4 key points to clean well. First one is clean window from top to bottom. It's like from top to bottom, and squeezy tracks the scrubber. It's squeezy tracks the scrubber. Always scrubber is forward and squeezy track the scrubber. And third one is to keep touching during cleaning same column. So scrubber and squeegee need to keep touching during from top to bottom during cleaning one column. And force is power to one section is like these pictures. After cleaning the one column, we move to second column and third column. But we cannot go to second column to one column. Then it's no good. So these figures are solution of this issue. The solution consists of module robot which install the squeegee next to the scrubber and its swarm robotics system to control modules systematically. So control one module 2 down, the next module 2 down, and the next step is module 3 is down, and it's continue. And finally, the modular robot strategy is proposed. Our strategy consists of both type module installing a cleaning unit and its swarm robotics system. The module proposes an ability to change its cleaning area by controlling foot location and moves from top to bottom along window frame with overcoming it. So this is a module robot, and this red one is a cleaning unit. So cleaning unit, keep touching during moving, then we can accomplish that cleaning. So next, the module robot is developed. This is our developed module robot, which for this biprototype morphology. And the key point is module installs parallel linkage mechanism to keep mechanically the foot unit and the glass surface parallel. Of course, the glass surface is always flat, so we don't need to change to control the angle against the glass facade. So our idea is mechanically fixed to keep parallel against the glass surface. And mechanical bar to break a vacuum in suction cup is handled by RC sub motor via hand mechanic, actually in this diagram. So we can control if our plan is to break the vacuum when the robot walks, disattach from the glass board, and when we want robot attach the board, we switch to vacuum. After that, to control the developed module, project regenerator is designed. This project regenerator works for locomotion of individual module. In order to satisfy our modular robot strategy, the mobile module basically locomotes with respect to each step, like a general bike robot. Of course, you know the general bike robot works if from this situation, the left foot overtakes the right foot, but in our strategy, left stopped the side of right foot unit. In this based on this assumption, The trajectory generator consists of these three algorithms. One is gate generation and foot trajectory generation and angle calculation. Firstly, the gate for the grasshopper cleaning is discussed. To prevent improving edge of the suction cup approach to the glass surface vertically for engaging and disengaging. So this is the example. If the suction cup engaging not vertically, then it may involve the edge of suction cup. Then suction cup cannot adhere appropriately. So suction cup should approach to the glass surface vertically. Then suction cup can appropriately adhere against the glass wall. And to start from simple algorithm to avoid complexity, relative gate of right foot unit is generated by setting a reference point on left foot unit. Then just bring up right foot and move it forward. Then move, right foot move forward and put it bring down it, then and attach adhere the right suction cup to the wall, and bring it down again. Then relatedly, the left unit is bring up, and right foot move backward. Then relatedly, left foot unit move forward, and bring the right foot unit up. Then then the robot has accomplished to walk one step. And so the target position is changed in sequential order. Start from here, then next target is here, and next is here, here, here. So target position is changed in sequential order. The sequential, so we set the target position sequentially, and this table is a sequential target position in. And in this sequential algorithm, gate direction is adapted corresponding to the indicated position. For example, if the indicated position is minus for the x, then left unit should move fast. Should move before the right unit. Then we change the rotation direction. And this algorithm can change automatically. The continuous trajectory between each sequence is generated by utilizing the fifth polynomial interpolation. The fifth polynomial interpolation is formulated as this equation, and its coefficients are calculated by utilizing these equations. And finally, target angle of each actuator to realize target position of the robot in the foot unit are calculated by utilizing impulse kinematics with these equations. Thus, in this trajectory generator, the target position to generate the gate is set in sequential order, and the continuous trajectory is generated by fixed polynomial interpolation. After that, the target angle of each actuator is calculated by impulse kinematics. That is an algorithm of the design trajectory generator. And it is verified that the developed module robot is capable of locomoting on glass surface by design trajectory generator. This figure shows a system architecture of this experiment. CM700 A performance main computer include the communication between other components and trajectory calculation. This movie shows the experimental result. We can touch to the ball and then we can one step is done and move to second step. And this is a obstacle supposed to the window frame, and the robot can overcome the obstacle. So we have success to develop the efficient 5-type module robot. However, we need to operate the target position, target step position by ourselves. So the foot location algorithm is constructed. We set 3 assumptions to simplify the problems. One is our window frame is arbitrary quadrat group. The coordinate of the window frame's vertex are known, so its 4 coordinates are known, and the window is much bigger enough than the robot. And we have found these 4 requirements to accomplish the faster cleaning appropriately. First, since the cleaning liquid fall down from top to bottom, the cleaning is also done from top to bottom. Next, move to the second palm and clean the window again. However, matching opposite side of the cleaning unit may escape the cleaning liquid as is figure. So our idea is to slide the cleaning unit and to make overlap a little onto the right cleaning area. Then the cleaning can be accomplished without escaping the cleaning liquid. Thus, this algorithm overlaps the cleaning area of both cleaning unit a little. In addition, of course, the algorithm must avoid the collisions with the window frame. From the assumptions and requirements, the algorithm is able to categorize into 4 situations. First is set the cleaning unit on right top, and second is walk with a maximum stride distance. Third is set the left unit so that its cleaning area overlaps a little. Number 3. And fourth is set the right unit with avoiding collisions with window frame, bottom window frame. And these situations are able to formulate by considering geometric constraints between the robot and window frame. And we have constructed the algorithm based on this idea. This is a simulation result. The X marks represent the determined foot locations, and T-like shape represent the foot unit of the module robot, is shown in this figure. And this animation shows the algorithm calculates the foot location along the right window frame, and the area of both left and right cleaning unit are overlapped a little. You can see here, and here. And thus the algorithm determines the appropriate foot location satisfying the geometric conditions. And this is conclusion. The modular robot strategy for the gas pattern cleaning robot has been presented. The modular robot has been developed, and the trajectory generator for locomotion of individual module has been designed, and effectiveness of the module robot and the project generator has been verified via the experiment. And the good location determination algorithm has been constructed corresponding to the geometric functions. And thank you for your attention. And if you have any questions, you can email me, and I can answer. Thank you.
Thank you, Professor Nansai, for introducing us to the glass facade cleaning solution, which was modular and an introduction to the kinematics and control involved with it. So I would like to invite now participants to ask questions related to the presentation. They can open their mic and ask question with Professor Nansai.
Hi, Professor Nansai. I have a question regarding your inverse kinematics. We wanted to know that is the inverse kinematics is solvable for all condition, or is there any singularity, and we have to you have to satisfy certain constraints such that inverse kinematics is solvable?
In this situation, as shown in this figure, the robot can assume as a Turing manipulator, and then so almost there's no singular position. So we can solve inverse kinematics without any issues, no single position.
Okay, thank you, sir.
One or two more questions from the audience. Still have time.
Yes, I am Kumar Duraraj. I want to ask a question. Hello?
Hello?
Are you able to hear? Yes, I am Kumar Duraraj from Trust University. I want to ask a question.
I'm sorry, I'm very noisy. So can you speak slowly, please?
My question is on any simulation platform for practice.
I'm sorry.
Yes, simulation platform.
Yeah.
A simulation software platform for practicing open source gain. Can you suggest?
Can you type in chat? Yeah, I can answer.
Okay.
You can write your questions and then because the voice is noisy. So I suppose
you mean the simulation software or something? I use Matrix, which is like MATLAB. MATLAB like free software I use for this simulation.
I posted the simulation platform for practice.
the voice is not clear. You can write your question.
I posted my question. It is available at the chat box.
Sorry, I'm sorry, I cannot catch due to that noise.
Yeah,
so
even sorry, even I cannot understand. So if you can write it, it's better, or else we can conclude this today's session and then ask Dr. Christie to have the concluding session from his end. So if you can quickly write your question in the chat box, we will take that.
For section, I don't check any pressure. Just we control the vacuum pump by RC servo. So we just switch on the vacuum, switch on the mechanical valve systematically using servo motor. Practice? What do you mean the practice? Simulation platform, you mean the software notes, or you want to ask the computer specification? I use MATLAB software.
Okay, thank you, Professor Nansai. So we have also one suggestion from Professor Saha. So he has his Roboanalyzer software name is Roboanalyzer, which is available online, and it is very useful for learning and teaching robotics. And similarly, the MATLAB-based ReadySim software is there to solve the dynamics of the serial systems. Even it can solve up to like a serial chain manipulators up to 10,000 or 20,000 links. So it has a fast solver which can solve the both forward and inverse dynamics. So and Professor Nansai has his also publication on the dynamics of Theo-Jensen mechanism, and he has used uh, Newton-Euler approach, right, Nansai?
Oh yes, thank you.
Yes. So especially you can refer also Professor Saha work with he has a decoupled natural orthogonal matrices concept which he introduces for solving forward and inverse dynamics that you may refer. Yeah. So again, thank you so much for your presentation, and now we pass on to the Dr. Christie from Priest University to conclude today's session. And thank you all the speakers and all the participants, and especially to the speakers that they came on time, and each session went as per schedule. So thank you so much. And it's now over to Dr. Christie, who will conclude the session. Thank you.
Thank you, Mr. Amir. Am I audible?
Yes, sir, you are audible, and your video is also coming.
Okay. Thank you. It was marathon day today. There were a total of 16 sessions, 16 sessions we had. At the outset, to begin with, again, I would like to thank Dr. Amir, Dr. Satyan, and Mr. Balakrishnan, who were there throughout, holding the fort. It was such a great support from their side for us to have them on board, and very wonderfully they have coordinated the whole day's session. So thank you very much, Dr. Amir, and the whole team has worked under the able guidance of Dr. Rajesh Mohan Elara, and we are very thankful to you from Prest University on behalf of the Chancellor, the Vice Chancellor, the Registrar, our advisor, and on my own behalf, I would like to thank the entire team at Singapore University of Technology and Design for the wonderful coordination which they have done. And we hope to receive the same support during the 2 coming days also, when the sessions are going to continue. We started with Dr. Ami Eguchi's session. Very rightly, the whole day session was handled mostly by academicians. So it was very, very apt that Dr. Ami Eguchi started the session with the topic robotics as a learning tool. How in education very efficiently robots can be used. We started with that. The second session was by Dr. Hayat Amir from, again, ACTD, the hero for the day, I would say, who has so valiantly coordinated. I don't know whether he had his lunch on time, breakfast on time. I wish that he will have dinner on time, Mr. Amir. And he spoke on the taxonomy of self-configurable robots. And the third session was by Dr. Gary Archer, neuromorphic computing for robotics, and he spoke from the neuromorphic computing laboratory. And the fourth session was by Dr. Madan Mohan Raiguru, control and optimization in reconfigurable robotics. He explained the optimal path tracking with constraints. He spoke elaborately on linear state space system model. And he also discussed a solution for trajectory tracking method in detail in his lecture. Mr. Narendranath Bhaskar carried out the the fifth session, and he is a researcher at Singapore Singapore University for Technology and Design. He gave a very clear explanation of key performance indicators, and he beautifully connected it with the heartbeat of the robotic system. We must thank him profusely for having accepted to join in at a very short notice as Dr. Kannan from Khalifa University, Saudi Arabia, happened to withdraw due to unavoidable circumstances. And the sixth session, Robotic Vision, Past, Present, and Frontiers, was by Dr. Arnab Sinha, the Tata Consultancy Services, Kolkata. Seventh session was by Sajid Nizar, Junior Associate Professor, and his topic was toward haptic surgical robots. He's from the Kyoto University of Advanced Science. He explained the prototype of a surgical robotic manipulator, haptic devices, and exoskeletons were dealt with in detail, along with a psychophysical experiment. The haptic solution he suggested for the on-road traffic situation was quite interesting. And the eighth session was handled by Dr. Rajesh Kannan, Amrita University, Kerala, South India. He gave a very good details of specific applications, human-centered applications like Bodhi, Prabha, Maruti, which can be beneficially employed in the present pandemic situation. It's of interest to note that this laboratory is turning out products that are intensely human-centered. And the ninth session was by Mr. Kannan Madhukumar, the CEO of Oceania Robotics. He spoke on ship repair activities where plenty of avenues exist for robotic applications. The blasting process carried out using a robo for paint removal on a ship hull, a robotic floor cleaning, and the false ceiling inspection robots were some of the demonstrations that he gave us. And the 10th session was a walkthrough of the Singapore University of Technology and Design robotic related facilities. The 11th session was by Dr. Douglas Beckel, University of Santa Catarina of Brazil. He spoke on mobile robots. He dealt in detail with a particular model called Baxter and Sire model robot. And we had Mr. Yogesh Krishnaswamy Tamil Selvam from Canada, University of Western Ontario, for the 12th session. And his talk was on self-configurable cleaning robo, facade cleaning robo with deep learning-based crack detection. And we had from IIT Delhi, India, the Department of Mechanical Engineering, Dr. Subir Kumar Saha, and he very beautifully explained how he takes robotics to the rural masses, which is a very, very essential topic in the Indian conditions. And we are so thankful to him for the very practical lecture he gave and the way he explained about his laboratory being involved in matters related to the rural masses. And 14th session, we had Dr. Acosta Calderon Carlos Antonia, technology leader in robotics, Department of Electrical and Electronics Engineering, Singapore Polytechnic. And to put a full stop for the day, we had Dr. Shunsuke Nansai from the Department of Advanced Machinery Engineering, Tokyo Denki University, and he spoke on glass facade cleaning robot. It was a marathon day, and it was so wonderful for us. I'm very sure those of the researchers, faculty members, the industrialists who were there would have really enjoyed the day. And the whole session has been recorded, which will be made available to those who need it at a later date in time. And we are very, very hopeful. Day 2 is going to be more elaborate, still more energetic, and I'm sure our team will take it forward into the second day also. Once again, thanking everyone who attended, and in particular, Mr. Amir, Mr. Satyan, Mr. Balakrishnan, and the able guidance from Dr. Rajesh Ellara. I wish to close the day. Thank you, one and all. Thanks.